Okay, we're going to start out by going through the assignments. How did the assignments go? Did it go well? Was it too hard, too easy, you needed more, or was it good? Had some problem with the texture stuff. Yes, the texture part it's a little tricky because there was one more step involved that I didn't predict would actually happen because I forgot. I wrote the assignment without actually doing it myself, but there was one more step in there that I didn't anticipate, and it can be kind of confusing because of the way that we use the texture in this assignment. Less than 99% health, exactly. So basically there was an issue where if your health bar has full health or no health, or rather you're above a threshold or below a threshold, the texture sampling does not look correct. So that was something that I didn't anticipate would happen. It makes sense that it does happen, and we should talk about that. So the goal of this exercise was to make a health bar in more and more advanced ways. So we start with a very, very basic health bar. The idea is that you have some rectangular area, and you want to make that fill up with some color. You want to start at a red color when you're low health and end with a green color when you have a lot of health. That's kind of step one. So let's just do step one. So just going to make a new shader. Oh, I wonder if I should separate these by folder in case I share this later. There we go. Lesson 1. Lesson sounds so formal. I don't like the name of that. Stream 1. There we go. That's better. Let's make a new folder. Stream 2. Lecture. Who knows? Health bar. And then we'll make a health bar material. Call it health bar. And then we make the health bar mesh. In the assignment, you could just use a quad, the built-in Unity quad, and then scale it. Episode 1, that works, yeah. I set the texture to a sprite 2D and that solved it. Yeah, that is kind of the wrong solution, but I'm glad it helps, yeah. Because you're not using it as a 2D sprite in this case. So it should probably be left as the setting it was on before, the default import setting. But yes, you do want to set it to clamp instead of wrap. And I will talk about why. So we have our quad. It's a very empty health bar right now. So let's add our health bar material to it and then open the shader. Okay. I feel like I should just set up a default shader. Because I do this every time. Just fixing the brackets, removing fog, because I don't care about fog. It's just messing up my stuff. It's not even hard to do it. I just never do it. Okay, let's see. Mesh data. Interpolators. You can set writer to fix the brackets for you fairly quickly. I don't know how to set auto formatting for shaders. I didn't find that setting. I found auto format settings for everything else, but not shaders. So if you know where that is, do let me know. Let's use float, full precision. Okay, let's see, what else? So this Unity transform text macro is kind of actually not needed here. We're never ever going to change the tiling of the texture. So in this case, I'm just going to remove that because it's useless. We don't need it. And then by extension, we don't need those parameters either, the scale offset parameters. So I'm just going to delete that. And also, if you do that and you go back to Unity and you select your thing, you can see that you still have the tiling offset parameters here, even though they're not used. So one thing you can do is that you can add an attribute to this. I think it's no scale offset. And then if you add that, then you don't have those parameters there, which is good, because then people are not going to be misled by unused parameters. Okay, so the first step of this one was a health bar that should go from, let's see, there you go. A health bar that should go from red when it's low health and green when it's full health. So let's start with that. And every time you do stuff like this, it's usually quite good to try to break it down into separate pieces, right? If you think about what we need here, we need to, where did the document go? So we need to have some mask that is increasing across this one, as in it's just white where the health bar should be and black where the health bar should not be. And the term mask is going to be used like all over shaders, because the concept of using a mask is super, super useful. Generally what a mask is usually a single float value. But again, it changes across all of your pixels. So you have some area that is white, some area that is black, and then usually you use that to blend between two different states, right? And in this case, we are blending between the color of the health bar and whatever color we want as background for the health bar. In this case, it's black. So we should start out by making that mask, as in we want to have a health input going from 0 to 1. And if we change that input, we should get just a white health bar that is increasing across the black background, right? So we need a parameter for that. So let's add that. Let's call it health. And make it a range from 0 to 1. I cannot keyboard right now. Start at 1. Add the variable. Okay, so the default shader samples a texture, but we're not going to do that in this case. All right. So now we want to create a mask out of this. And we want this mask to change as you change health on this thing, right? And usually when you're talking about things that are changing across either space or time, one of the things that you should pay attention to is across what does it change? So a useful way of thinking about this, I did not have Photoshop open, should have opened that earlier. Okay, so whenever you're thinking about these types of things where something is going to change across some space, right? The health bar, we have some sort of rectangular area, and the direction on which all of this is going to change is horizontally, right? It's going to change across this space. So generally what that means is that you then need access to some sort of coordinate system that does change across that space. The same thing goes for, I guess you can call this just a horizontal. And it's a linear change, right? But then there are other like spaces you can change things across, right? If you have a distance value, say you draw this thing, this one is brighter in the center, but it's darker in the edges, right? So this thing also changes the way it looks, but this time it's radial. So it changes as you go away from a point, right? So sometimes it's useful to keep these in mind. So you have like linear changes and horizontal changes. And in this case, it would be a radial change. And the same goes for like gradients. You would call this a radial gradient. This would be a linear gradient in case you're blending between two different colors or something. And then you also have angular, which I hope we can. Why is that a fixed size, Chris? Gradient tool. There we go. Basics. And then you have an angular gradient like this. So angular. In this case, you can see that it's changing by the angle to some reference point. I guess I can clarify it by doing that. There we go. Just to get our terminology straight, this is a radial gradient because everything changes by the radius. Nothing changes by the angle here. If we go around this angularly, the color is the same, right? So it doesn't change by angle. Same with this one. This one doesn't change by radius. If we go out or closer to the center, it's all just the same color. So the domain over which everything is changing is depending on the angle toward the center. That's why this is an angular one, and this is a radial one, right? And quite often, when you're making shaders like this, you can swap these out, and if all the math following that is the same, everything is still going to work. So even if we finish this health bar, we can then just change what type of gradient we have. If we want to make a radial health bar or an angular health bar, it's relatively easy to just swap between these different types of things because shaders are just non-destructive, right? We don't have this baked into a texture or anything. If we change the inputs, we just change the outputs, right? Anyway, I just wanted to quickly mention that. Oh, and obviously if we're talking about a gradient, I didn't actually draw the gradient in this one. There we go. All right. But in this case, we want a linear gradient, and we need some sort of coordinate space that changes across the x-axis, right? And pretty much most meshes that you make, depending on how the mesh is made, of course, you usually have UV coordinates, and we talked about that during the previous lecture. UV coordinates are usually, not always, two-dimensional coordinates in your mesh data. And we can display that by outputting it as a color if we want. So return float 4 because our output of the fragment shader is a float 4. And we can just grab the UV coordinates from our interpolators. So that's going to be I.UV. And then we can just add 0 for the remaining channels. And we're going to get these gradients. So what we're visualizing is the UV coordinates for this mesh. And you can see that it goes from black to red at the bottom. And across the left side, it's going from black to green. And as usual, the X and Y axes can be visualized using color. So then X corresponds to red, Y corresponds to green. So this is a linearly increasing gradient of red. And this is a linearly increasing gradient of green that are then added together. And when you're dealing with colors, red plus green is yellow. Yeah. Because generally colors add just the same way as vectors. So if you have a red color, then that will be 1, 0, 0, 0. We can skip the alpha channel because it doesn't matter. And then green would be 0, 1, 0. And then if you add those together, it's just going to be like any other addition formula, right? You add them component by component, and then you end up with 0, 1, 1, which is yellow, right? So if we then visualize one of these channels, it's a little bit easier if we just do a single line for that. So I.UV.X, we now see the X coordinate of the UV channels. Or the UV coordinates. And you can do the same for the Y coordinate, then we see the Y coordinate of this. All right, but we're gonna make a health bar, so that's across the X-axis. So this is the gradient that we're interested in. So then we can then use this in order to, make something that changes across this space. All right, so let's see, we do have our health value. Okay. So what we then need to do is then create a black and white mask. We want this one to be white where the health bar is, and we want this to be black where the background is. You could also flip it, doesn't really matter, as long as you use the mask correctly when you're blending between the two states. All right, so a very simple way of checking this is that, I guess first we can make a variable for this. So float health bar mask. We can then check our X coordinate, and then we can use our health value. And one thing you can do that we mentioned earlier is that you can, if you make comparison operators that return a bool, that bool can also be automatically cast to floats. So true would be 1 and false would be 0. So we can turn this into a comparison. So if we want this one to be white, where your health value has reached a certain point, then we can just compare the health to this coordinate. So we can check if health is less than the current x coordinate being rendered. And remember, the fragment shader is run for all the pixels that we're rendering, right? So this is going to happen for every single pixel that is going to render on this object. Okay, and then we can output the Healthbar mask. There we go. So right now the mask is inverted. So because I wanted white here, so we're gonna have to flip this. But you can see that the mask now changes depending on what health value we're using here, right? So better to use floats than ints. In most cases, I don't think it actually matters, but I mean, you would use whatever is appropriate. I think in some cases it might compile to floats regardless, but I'm not sure about that. But yeah, but what would be the use case for integers in this case? Are you thinking about like if you have a health value of like 500 or whatever? I think in cases like that, what I usually like to do is that I usually like working with normalized ranges. So I like it when I have a range that is just 0 to 1, because then the math becomes much, much simpler on the rendering end, because then we could just do this comparison. If we had like a max amount of health, we would need to remap that before we use it. But that's just a personal preference. You can do it whatever way you want. Because float is either 0 or 1, I was just thinking ints would be what to use because bools. Oh, I mean, I guess it doesn't really matter in this case. Because right now we're not doing much with this anyway, but I think there might be some platforms where like mixing integers and floats might be slow, but I actually don't know if that's true. I just seem to remember reading something about like sticking to just using floats or using the same floating point precision and not mixing a bunch of precisions and data types, like avoids having to convert between all the different things. Not to mention that I'm pretty sure that integers are not supported on all platforms, like on mobile or whatever. Right, so now we have the Healthbar mask. So this is just the black and white mask, and I also wanted to invert it. So let's flip that. There we go. And then we also wanted to change the color of this health bar depending on how much health you have. So if you don't have a lot of health, we want this to be red. If you have a lot of health or full health, we want it to be green. Okay. So let's define the health bar color, right? Health bar color. So the color of the health bar only depends on how much health you have. Where we are on the health bar doesn't actually matter. We're just interested in how much health do you have, and you blend between these two colors, right? So I'm just going to hard code the colors into this. So the health bar color in this case is going to be, we're going to use lerp because we're going to blend between these two colors based on how much health you have. So health is then going to be the t value of the lerp. And we're going to blend between, if you have low health, that's red. So that's going to be float 3, 1, 0, 0. And if you have a lot of health, then it's going to be green. So float 3, 0, 1, 0. Okay, so now we have the color of the health bar, but we're not actually using it. But we could also make sure that it works if we want. So return float 4. If you can spell, that's the difficult part sometimes. Okay. So we got the color. If you have low health, it's 0, it's red. If we increase it, I can see that it goes toward green. So that seems to work. Cool. And then we might want to set the background color, right? In this case, we're actually, I'm just going to do BG color, too long of a word. And that's just going to be black in this case. Okay. We can then use this mask to blend between these two states. So if we look at the mask again, we can use the mask itself in the t parameter of a lerp, right? So now then we would blend between the background and whatever we want here, right? Because remember, if you have a lerp, then wherever the t value is 0, we get one result. Wherever it's 1, we get the other result. And any values in between are going to be interpolated, although we're not going to use the interpolated values in this case, right? I wrote vector when I assigned all my variables. Is there a difference between using vector or float3, or does it have to be a conversion if you use vector? I have never heard of vector, so I have no idea how that works. But I imagine it would do some type conversion. I don't know. I wouldn't expect that to compile. So I don't know. Okay, so let's blend between this to get the final Healthbar color output. So float3, out's color or output color or whatever. That's going to be a lerp between the background color, because the first parameter of the lerp is where it's black, and we want the background where this is black. Obviously, since the background is black right now, you could take a lot of shortcuts here, but we're not doing that, just to show how the interpolation can work, right? Okay, so lerp between the background color and the Healthbar color, based on the Healthbar mask. All right, and then we return the output color. There we go. So now if we reduce the health, you can see that it goes red, increase it, and it starts going green. All right, any questions so far? I saw it on a forum after getting frustrated that just parentheses didn't work. Oh, yeah, so there's a very like frustrating and common mistake that you do. Like if you have float3, some color, then the way to write that color is using float3, and then you write, you know, some values. This would be HDR. That's really weird. Okay, so a very common mistake is that you sometimes forget to write the variable name. And the frustrating thing with this is that this actually compiles. This is valid code. And the, yeah, and this is the comma operator, which is a really, really cursed garbage operator that has been frustrating me a lot, and I don't see the point of it existing at all. Apparently there are some cases when using for loops where it might be useful for whatever reason. I don't know. It's garbage, and not great. I have a ton of questions, but none of them are useful. Oh? Well, in that case, I guess I shouldn't answer them. Yeah, the comma operator is cursed. I'm curious about Yuan's question. Wait, what question? Oh, I didn't know that that was a question. Sorry, I thought that was just a statement. How would you go about if you wanted Healthbar that changes in chunks? So in that case, I guess what you would do is that you would sort of posterize the coordinate values. So it would probably be something along the lines of, so if you take the x coordinate multiplied by 8, or rather you floor that multiplied by 8 and then divide it by 8. I believe we will now have it split up into 8 parts. Yeah, and then if you wanted to add that mask around it, because in your example you have like a black border, you could map a repeating texture to this that lines up with all of these chunks, right? But I'm not sure if you would want to have like a floating point value that can sort of fade like this, even though it doesn't actually change the chunks. But yeah. Going with 1 minus Healthbar mask times background color plus Healthbar masks times Healthbar color is performance-wise pretty much equivalent to the built-in lerp function, right? Yes, that is equivalent, yes. But I mean, if you do write that, then you should be using a lerp function, because otherwise your code is less readable, right? And yes, so like you're mentioning, it can overshoot with a built-in lerp function in shaders as well. If you do stuff in Unity, then you might have used math.lerp before. The Unity math.lerp is clamped, but the shader lerp is unclamped. which means that if you go outside of 0 to 1, it will extrapolate those values. So it's important to remember that they work a little bit differently. All right. So there we go. Got the smooth health bar again. So let's move on. All right, so we have set up this, the very basic 1A part of the assignment so far, where you just have this very simple health bar that changes from one color to another across the space of this one as you change the amount of health that you have. The next part of the assignment was to add a threshold so that you can set where it's going to go fully red and where it's going to go fully green, meaning that if it's under a certain value, it's going to be fully red. If it's like if it's less than 20%, for instance, then we just want that to be the bottom color. And if it's above 20% or so, we want it to be fully green. Okay, so what that means is that we basically have two thresholds, right? Where we want to change the value of this one. Then what we need to do is that we need to basically remap the range at which we are interpolating these colors, right? Because we have the, or no, sorry, not the color, but, or no, yes, it's the color, sorry, I'm confusing myself. This one. So we want to set thresholds for, depending on how much health you have, we want to select the bottommost color or the topmost color. But instead of doing that at the very ends, we want to remap this. Okay, so the way to do that is using our very familiar function, inverse lerp. Because now we have a range of 0 to 1, but we want to make it so that at 0.2, we want it to be 0, and at 0.8, we want it to be 1, right? And that's the perfect use case for the inverse lerp. We don't have an inverse lerp, so I guess we should add that. I keep just re-adding it all the time. I should really make a library. What an inverse lerp. Okay, so then just for the color interpolation itself, we want a different t value for this lerp. How do you make a shader library? Just like you can include Unity's CG include here, you can make your own CG include file where you just write functions. So then you can just include your own like library stuff. Super useful. It can also be really, really confusing if you overdo it, kind of like Unity has done in HDRP and URP, making your shader pretty much unreadable, which is not great. All right, so this is going to be the t value for the health color. So we're going to inverse lerp between these thresholds. I'm just going to hard code them now. So at 20% and at 80%, I want to remap the health value so that it's wherever the health is 0.2, I want this to be 0. Wherever health is 0.8, I want this to be 1. That's how the inverse lerp function works. So, so then we have the t value for that, and we can input that there. One thing to watch out for, though, is that, like I mentioned before, the lerp is not clamped. So t health color is actually going to shoot over to negative values if we are below 0.2. So we might want to make sure that we clamp this, which, confusingly enough, is called saturate. So that saturate will clamp it between 0 and 1. Kind of tempted to just like, there we go. Or wait, other way around. It's a little cursed. Probably shouldn't do that. Okay. So now we're clamping this between 0 to 1. We have the remapped health color. And then let's see if it works. Okay. So you can see that it's changing to red here, and then it looks like it's stopped now. So that's exactly what we want. So now it's fully red, even though it's changing within this range, and then it starts changing above that threshold. And then once it hits the top threshold, it's fully green. It's not fading in this range, which might be useful if you want the health bar to like make it feel like you still have a lot of health and that you're not like yellow even when you're here. So that's kind of a design choice, I guess, but useful nonetheless to have that ability to tweak those thresholds. Although now I just hard-coded it, so. Okay, the next step was to, instead of making the background color be black like this, we wanted to instead make it transparent, as in not render at all. There are many different ways of doing this, depending on your use case. We can either make an alpha blended shader, or we can make a, still leave it as an opaque shader, but we just discard the pixels. So what you can do is you can use a function called clip, which is a very, very special function. Clip will basically, depending on if the value is less than or equal to 0, it will discard the current fragment being rendered, as in it will not output at all. So we can actually do this based on the Healthbar mask. We might need to, actually it might be only if it's less than 0. So we might need to subtract some small value, yes. Sorry, so it's if it's less than 0. All right. Or probably 0.5 is probably more safe in this case because we don't have any grayscale values in between. So now it just doesn't render that part of this at all. And we can still modify this one however much we want. One of the advantages of using clip as opposed to alpha blending is that when you use clip, you can sort of kinda make transparent shaders without having all of the sorting issues that you generally get with transparent shaders. The problem is that you can only have like 1-bit transparency. Either the fragment is rendering or it's not, right? There are ways to sort of make things look like they're fading. So some games use like dithered fading in order to get like gradient looking things that can like have partially faded stuff. But the nice thing about this one is that it sorts perfectly because it still writes to the depth buffer. It still reads from the depth buffer, unlike the transparent shaders that just can't write to the depth buffer, or they can, but generally you don't want that. Yeah. Okay, so that's just one way of discarding fragments. But all right, we should probably do the alpha blending version of this too. So that was clip. I can leave that in, I guess. And I guess if we want to optimize this, I guess we should shuffle things around a little bit because we probably want to clip as early as possible. When you say 1-bit, do you mean where the alpha mask is either black or white and not different shades of gray? Yes. When you're when you're discarding fragments, there's no partial transparency. It's only either the fragment renders or it doesn't render. There's no way to make it like halfway blended or whatever. It's only either rendering or not. So that's the disadvantage of using clip, is that you can only tell it to not render or just render it. There's no way to make it like faded with alpha blending or whatever. So let's do the transparency version, just using alpha blending. So right now this is an opaque shader, and we don't want this to have the render type opaque if we're doing something that's transparent. So we want to set render type to transparent. We also want to set a render Q to transparent. Because that way, we generally always want transparent objects to be rendered after all the opaque objects. The reason for that is that most transparent objects still want to read from the depth buffer. Because if you have something that is transparent behind something, you still want that to not render, right? Or if it's intersecting with something, you still want it to not render on top of other objects like that, right? All right, so we want this one to still be transparent. or to make it transparent rather than opaque. This also means that we probably want to change the way that it behaves in terms of the depth buffer. Because we don't want this one to write to the depth buffer anymore, because even though we might set it to transparent at some place, we don't want to write to the depth buffer there, because then other transparent objects might discard their pixels, and as soon as we have overlapping transparent stuff, you pretty much never want to make the transparent stuff write to the depth buffer, because then they're going to discard each other and it's going to look like they just delete themselves as they like overlap other things. It's going to be a mess. So generally you don't want them to write to the depth buffer. So we add Z-write off. Okay. All right. And then we also need to set the blend mode. So if you remember, the way that the blending stuff works is that we basically have the source color, as in the color of this shader, times X, let's just call it X for now, and then plus the destination color times Y. The stuff that you can change with the blend modes is you can change X and you can change Y, and you can also change the operator here. It can either be plus, it can be minus, it can be a reverse subtract, which is just flipping the arguments. But generally, this is the formula that you're working with. So if you can set X and Y, the way that you usually do alpha blending, there are other ways of doing it if you want to look into like pre-multiplied alpha blending, which is a whole subject on its own. I'm not going to go into that. But generally, alpha blending means that you want to do source times the alpha channel of the source, and you want to do destination times 1 minus the alpha channel of the source. And if you look at this formula, this looks almost exactly like a lerp, right? This is a lerp between source and destination, right? Based on the source alpha as the t value, which is exactly what we want to do, right? So the way that you do alpha blending is you do blend src alpha 1 minus src alpha. There you go. So this is alpha blending. And then we need to actually write to the alpha channel, because now we haven't done that yet. So I guess just to see if it works, we can do a little test. What is source and destination in this case? Source is the color output of this shader. Destination is the existing color in the frame buffer that we're rendering to. In other words, the background, right? So you can think of destination as the existing color of all the things we're rendering to, and source is the color of this object. All right, so first we should probably just make sure that this works in the first place. So let's try return float 3, no, float 4. Let's make a red color, and then we set the alpha channel to i.uv.x. So now we should have a horizontal fade, right? There we go. So you can now see that we do have partial transparency as we move across this shape, right? Neat. So that works. We do have something that's alpha blended now. And yep. So again, slapping in these like return some color is pretty much just the easiest way to debug stuff in shaders. It's usually like good practice to just double check things every now and then like this, just to make sure that you got everything right. Because sometimes in context, when you have all of your code running, it might be a little confusing and hard to debug. All right, so then the goal was that we wanted to make this health bar. Let's see, alpha was 0, that's why that's not visible. So we wanted to make this one be fully transparent wherever the background color was here, right? So we can change a little bit in the way that we do this now. So instead of doing setting out color here and a background color, we're not going to need the background color anymore. So we can actually just remove those, and then we can simply have the health bar color in RGB, and then we can use the health bar mask as the alpha channel, because the mask is already black where we don't want the health bar to be visible, and it's white where we want the health bar to be visible, which is exactly how alpha would work in this case, right? So if we recompile, you can see that this is now transparent again, and we're going to change this one like this. And now it also supports partial transparency in case we want to do that, right? So if we, for instance, multiply this by 0.5, that means that wherever this one is 1, it's going to be 0.5 instead. So it's going to make everything a little bit more transparent. So now the health bar itself is transparent too. Yeah. Okay, so that we've done 1A, 1B, 1C. All right, you have questions, and you didn't want me to interrupt my explanation, so questions go. Is there a way to get the lines in the health bar fade? I'm guessing that's because of floating point precision in the UV coordinates. What do you mean by lines in the health bar? There are visible lines in the gradient when you did the transparent fade based on UV coordinate X. That could be just a video encoding, but it's also a limitation of that we only have 255 steps of transparency. So I don't know if it's video encoding in this case. I mean, it should be visible if we just return i.uv.x as well, right? Yeah, the lines you're seeing is probably mostly the compression, I would guess. Or it's just a limitation of the bits. Yes, I can show the blend function. There you go. Should you use clip to discard fragments early for performance reasons? When you do, how can you be sure that they will actually be discarded? So the way to test it is just to output a color, like some color that is very visible, and then write your clip function and see if they do get discarded, right? And then whether or not they will be discarded depends on what you discard them by. Like what is the parameter or values you use to discard, right? Yeah, and yeah, you can do that early for performance reasons, absolutely. So it sort of depends on platform as well. I think on some platforms using clip might be expensive, probably on mobile as usual. But yeah, so you can use that to optimize stuff out. I do that sometimes, even if I have alpha blended shaders, I sometimes use discard where alpha is 0 to early out in case I have like a really expensive shader. Okay, no more questions. Let's remove various stuff. Is it okay if I clean this up? I don't know if you want this code to still be here. I guess I can just watch the video if you want the old code back. Let's see, we make sure we got this restored. We do. All right, so the next step of the assignment was to use a texture for the color. I'm gonna, in this case, I think I'm just gonna bring back the background color instead of using transparency, because it's a little bit more easy to see how much health you have, I think. One thing you can do here, I'm just gonna set it to 1 for alpha. When you have a mask that is black and white, and you want to make it black where the mask is black itself, given how math works, when you multiply something by 0, it becomes 0, right? If you multiply by 1, it remains the same. So if we want the background to be black specifically, we could just multiply by the health bar mask, right? So in this case, it's just going to make it black wherever the health bar mask is black. Where the mask is white, it's just going to remain the same color. So if we go back now, you can see that it's still working. Okay, let's see, do I have yes, I have the health bar. Can I reset the settings on this? Reset, there we go. So now we want to use a texture that is then going to be defining the colors that we want. So you can see that this is a texture that has some like gloss effects and some shading at top and the bottom. And the color is now defined by the gradient inside of this texture instead of being something that we hard-coded into the shader itself, right? So yeah, so let's add our health bar texture. And let's go back to the shader. Now we can bring back the Unity default code. All right, let's just return the texture to make sure that it works. It does. So now now we got this whole texture mapped to the entire health bar, but this is not how we want this to look, right? We don't want the health bar to look like this, and we also don't want this to. If we take the health bar color, multiply it by the mask, this is also not the effect we want. So the goal of this one is that we want the entire health bar to be green when you're at the top. We want the entire health bar to be yellow when it's here. We want the entire health bar to be red when it's here, and so forth, right? Which is a little bit of a challenge, because now you need to think a little bit about how does texture sampling even work? And how can we make this sort of pick one slice of this health bar and stretch it across the entire health bar? So that's kind of a challenge that you need to figure out here. Also, because I don't like the way the compressed textures look, I'm just going to go to the texture and set compression to none, so we get some more colors back. Because I don't like ugly textures. It makes your texture like 4 times as big, approximately. Wait, no, not 4 times. Sorry, I'm thinking of something else. Actually, wait, 32 kilobytes. 5.4 kilobytes. Okay, approximately. No compression. There we go. So the point of this texture is that we want to extract the color of the health bar. That used to be this health bar color, right? So we move our color sampling there. So this is just to, right, this was for the T value. We don't need the T value anymore, right? Because we don't need that thresholding. So we can remove the thresholding. We actually don't need to blend between 2 colors either. So what we're left with is just our texture sampling. So there we go. Health bar color. All right. So what we're doing now is that we are sampling this texture. So something that is important to remember is that we can sample this texture however we want. We don't have to just straight up use the UV coordinates. We can multiply this by 2, and we have now just changed the way that we sample this texture. Obviously, this is not what we want to achieve, but the point is that the UV input to sampling a texture can be whatever you want it to be, for better or worse, I suppose. So what you need to think about here is that we want the color to be sort of picked from a vertical slice, right? Because if you have low health, we want the whole health bar to be red. So even if we are sampling over here, or rather even if we're sampling over here, but the health is currently at this point, or at this point, we want to pick the color from where the health is, right? So if you have a lot of health over here, for instance, like the health bar is cut off at this location, we want this part to also be green. So what that tells us is you can then again start thinking about across what does it change, across what does it not change. If we want to keep this glossy effect and the little shadows at the top and bottom, then we need the texture sampling to change across the y-axis, right? But we don't want it to change across the x-axis. Along the x-axis, we just want a single slice out of the texture. And the location at which we want that slice is your current health value. So if you have a lot of health, it's going to sample from the very green part. If you don't have a lot of health, it's going to sample from the red part. So what we actually want here is that we want the x-coordinate of the sample to be your current health, but we want the y-coordinate to still be the UV y-coordinate. So what we need to do is say floats2, where the health is the x-coordinate, and i.uv.y, which is the y-coordinate of the UVs, is going to be the y-coordinate. And then if we go back to the health bar, you can now see that we have a very murky health bar, which is a fun problem that we ran into. Okay, so you can see that now the health bar goes from green and it goes to yellow, and the whole health bar is yellow here. And then the whole thing starts fading to orange, and then eventually to red, and then the deep, dark, dangerous, you have very low health red, right? Okay, but now we have a fun, interesting little puzzle. Why does it go murky green as soon as you have full health? This is because the way that the texture is sampled, in Unity at least, that depends on the import settings of that texture, because there are different ways of sampling a texture. So right now, we haven't actually told Unity how we want to use this texture. So just to clarify a little bit what is happening. So if we just go back to the original UV sampling that we had, to just draw the entire texture. If you zoom in on the edge of this, you can see that there's a little sliver of green there, right? And if you zoom into the edge of this, you can see that there's a little sliver of red. The reason that this happens is because the texture thinks that you want to tile this. It presumes that you want to have multiple of these next to each other, so that it's making this very nice, pretty little blend between these colors. Unfortunately, that's not what we want. So this actually has an undesirable effect for us, right? Because when we sample a single slice out of this, we're sampling the halfway blend between minimum health and maximum health, right? So basically, this texture presumes that we want to repeat it when we sample it. So what this is called is that you say that the texture clamping is wrapped, as in it presumes that you want to repeat it along in all directions. But what we actually want to do is that we want to clamp it, as in if you go beyond one of the boundaries between 0 to 1, we don't want to repeat that. We want to just stick to the edge that we left from. So we just want to make those colors extend forever instead of trying to repeat this texture. You can set that in the import setting of the texture. There's something called wrap mode. And if we set that to clamp, it's now going to clamp instead of trying to repeat this texture. A very useful setting that they added relatively recently, finally, is that you can set this per axis as well, so that it clamps in one direction, but you might want it to repeat in the other direction, which is really, really useful, and I'm glad they finally added it. Anyway, so in this case, we don't want it to repeat because then we get this gross, blurry boundary. In this case, we want it to clamp. And we wanted to clamp in both directions. So if we had some sort of, if we had a bright color at the top and a dark color at the bottom, setting it to wrap would also destroy that effect vertically, not only horizontally. All right, so let's see if it works. We changed our texture to be clamped instead of wrapped. And then we set health to maximum value, and now it is fully green, and it is also not murky yellow when it's completely gone, which is just nice to know, I guess, in the back of your mind, even though it doesn't matter. But at the top, it does matter. So there we go. I'm still mega confused about this because it strikes me as a bit silly. What is the sampler doing? Is it sampling several points in the texture and taking the average? Shouldn't the sample of 1 be exactly on a pixel center? I'm pretty sure that depends on OpenGL versus DirectX, whether or not a sample is at the center of a pixel or at the upper left corner of a pixel. I forget how it works, but basically, if your texture is set to bilinear, it means that it's going to blend between the different pixels. So for instance, if we look at this grass texture, we zoom in a lot, you can see that it blends between all the different pixels in this texture, or texels, if we want to be really esoteric about it. So you can't actually see just one sharp pixel and then it jumps to the next, because this one is using bilinear filtering. So that's why everything is sort of muddied together and blended everywhere. You don't have to use that. But the problem is that you usually get a lot of aliasing issues. So you have aliasing issues and pixelation if you don't use blending like this. But you can turn it off if you set it to point filtering. Then you do get this like very pixelated, get a single color and so forth, right? But bilinear will interpolate between all the neighboring pixels. So that's why, so that's why it does this. When you say, shouldn't the sample of one be exactly on a pixel center? It sort of depends on how we, what color should be in the center of a pixel versus center of a pixel minus 0.5. Like if you offset it a little bit, it gets a little messy, but yeah. Now I understand why it's called nearest neighbor. Yeah, because then whenever you sample, it kind of snaps to the nearest one. And remember, whenever you sample a texture in a shader, you don't do that with integer values. You don't say, get this pixel, you say, get the color at some floating point coordinate, which could or could not be right on top of a pixel value, right? It makes zero sense to modify a texture by default when you've simply added it. What do you mean by modify a texture? Oh, the filter settings does not modify the texture at all. This is purely something that happens in real time. So this only has something to do with the way that we sample it. It doesn't actually modify the texture. And the default setting presumes that you want to tile textures, which quite often you do want to do that, right? Like, for instance, we have the grass texture here, right, that we looked at last time. We can set this one to clamp too, but we probably don't want clamp on this grass texture because then this is what happens, right? As soon as we go outside of the texture, it's just gonna stick to the nearest edge, right? Any other questions? Still can't figure out how health greater than i.uv.x works. It's a comparison, so it checks if the current health, which is between 0 to 1, is greater than the current coordinate, the current x coordinate on the health bar. So if it is greater than that x coordinate, it returns 1. If it's less than that, it returns 0. So then that gives us a black and white mask that we can use for blending. In my opinion, as much as possible, it should be explicit to avoid misunderstandings. Kind of have lerp in Unity is also clamping, like why linear interpolation is not equal to clamp. Yeah, but you can also get into disagreements about what that means, right? It's called linear interpolation. Why would you expect that to extrapolate when it just says interpolate, right? So you could argue that it shouldn't be called interpolate. So like, it kind of depends on like how you interpret that. So I don't know. I personally like it when they extrapolate because it can be useful. I don't need super bright lights anymore since I got this camera. So now my monitor is a big contributor to the color of my face, which is for better or worse. Not sure if this is good or bad. How do I get the math to be included in all new Unity projects though? Yeah, I guess you can't right now. I might make it into a Unity package at some point. I kind of just didn't. But maybe I should. Then it would be a little bit easier at least. There's a lot of shader convention I straight up dislike, like vertex shaders output V2F. Oh, fragmentators take a V2Fi. Oh, the O and I, the way that I read them is input and output. Yeah, so I means input, O means output. So then if I'm in the fragment shader, it's I, because I want to grab the input coming in from the vertex shader, right? But I mean, those are variable names. You can name them whatever you want. So if you don't like those names, name them something else. I think the shaders are sort of like notoriously annoying in that a lot of people who write shader code just use single letter names for a lot of things, which can be really annoying. But usually shaders are kind of limited and isolated. Like a shader very rarely has dependencies outside of that shader. So usually they're kind of self-contained and it's not usually a big issue. I think single letter variable names are okay in some contexts. If I'm writing an inverse lerp function, I'm not going to do start value, end value, and whatever. But in some contexts, I think it's okay to just have single letter variable names, but it depends on the context. I think in shaders, it's so established at this point that you use like single letter variables for the input from the vertex shader. So a lot of people are just used to it at this point, in which case, if everybody used to it, then it probably doesn't matter that much. but it's confusing as someone coming into it. Okay, there we go. Yes. Okay, it worked as I expected it would. It's as I expected. All right, so one of my students were talking about like, how does the bilinear interpolation work? Does it like discard the pixel data? Is it like in the center or is it in the edge? Like, how does it sample textures? In this case, I have a very, very simple texture. It's just a 4x4 pixels. And yeah, this is the texture basically. If I turn on bilinear filtering on this one, you can see that the colors are sampled in the center of each of the texels, right? There are little crosses that sort of happen because of how bilinear blending works. And then it starts interpolating to the neighboring pixels. And in this case, it's set to wrap, right? If we set the wrap mode to clamp, it's obviously going to clamp beyond the centers that go toward the edges. So that's sort of how it's going to, like, how it handles that situation. So if you want to read the top left color just cleanly, then yeah, you would need a half texel offset if you want to like still use bilinear sampling, but for whatever reason you want an exact sampling there. Any other questions before we continue with the health bar? No more questions. All right, we just did the texture part of the health bar, so that was 1D. All right, I only have 1E left, and the overachieving things, if you want to learn how to do that, which I think would be a good thing to talk about. So I think we should talk about those as well. All right, so the next thing was that we need to make the health bar flash or pulsate or like in some way animate the color of it or the brightness of it, whatever you want to animate, when you have less than a certain amount of health. Okay, so a very useful place to go whenever you want to do stuff like this. The first thing you want to do quite often is you want to figure out what do you actually want to achieve. Like if you want it to flash, how do you want it to flash? Do you want it to like have a strong flash and then fade and then strong and then fade? Or do you want it to be like a slowly pulsating, like a sine wave flashing thing, right? Because those are different curves to the flashing. So like answering that would be sort of the first question you should ask yourself. Then when you want to start tweaking things, a good place to like tweak stuff and like kind of figure out what type of flashing do we want is to define a curve for it. So then what we can do is that we can consider the x-axis to be time and the y-axis to be some sort of brightness value, right? So for instance, if we do the cosine of x, so now we have a brightness value that goes from 1 and then it goes back to -1, goes back up to 1 and so forth, right? So this would be a very soft pulsating thing, although depending on how we want to use this, we probably don't want negative values here. So because presumably we have some sort of color value, let's call it let's say the blue one is the color value here. Let's see if we can. All right, so the blue one might represent our color that we have. And then we want this like pulsating thing to affect this blue line, right? So how do we want this to be affected? So here you can start asking yourself, well, do I want to add or do I want to multiply? What do I want to do here? If you, for instance, multiply this by our sine wave up there, you can see that it's exactly the same because it's 1 multiplied by all of that stuff. I guess in that case, if we want to multiply, we can just visualize it straight up. We could add it as well, in which case the color is now going to go up to 2, which is going to be, it's going to oversaturate the colors, and then it's going to go all the way down to black, and then all the way up to white, and then continue increasing beyond that to even brighter. But this is probably too strong of an effect, right? If it's going to fade all the way to black and then up to something that looks you know, all the way up to something that just completely oversaturates everything, we probably want to tone this down a little bit. So what we can then do is that if we multiply this function we can reduce the magnitude of this. So if we multiply it by 0.1, for instance, you can see that this now has a much more softer pulsating effect, right? So now it goes from 1.1 as the max value and 0.9 as the minimum value across time. If you then want to change the speed at which this is happening, then you can multiply the input parameter to the cosine, which in this case is time, right? So if we multiply that by 5, for instance, the frequency has now increased. So we could make a variable for this called, I don't know. So maybe we can have A for amplitude. Actually, we can just type it in here, right? There we go. Frequency is going to be R, because why not? Okay, so basically we have these parameters now where we can set the amplitude of this. And the amplitude, we don't want it to be a 1 because then the flashing is going to be way too strong. So we want this to be kind of a low amplitude. And frequency kind of depends on, we need to look at this across time. It's kind of hard to like tweak these artistic effects without actually being in an engine. But this is a very simple way that we can modify some sort of pulsating effect, right? Okay. So let's do this in shaders. So basically we have our little mathematical function. And generally, a very simple way of doing this is cosine of time times frequency times amplitude outside of the cosine. And that's a very simple way that you can sort of tweak a sine wave to whatever parameters you want, right? So let's start out by just doing that flashing effect. So we got our health bar color, and we're going to ignore the mask for now. I'm just going to output the full health bar. Yeah, okay. So then we want this to flash, and we can then do our little sine wave again. So let's do float. Let's call it flash. So cosine of, remember that it's underscore time dot y for the current time that has passed in seconds. So it's the time multiplied by the frequency that we want this to be flashing in. We could either make this a parameter, we could hard code it, whatever we want. Let's do times 4, probably a good starting point. And then we want the magnitude of this one. The magnitude of this one, we mostly just don't want it to subtract all the way to 0 and then go like overblow the colors to like super saturated. So just some low value probably works. All right, so now we have this flash variable, and we could return the flash just to see if it works. That does not work because this is a float value, and it's going to take all of these values and spread them across RGBA. And because this is alpha blended, we don't want the A value to be 0. So we are going to set the flash dot xxx for the RGB values, and then alpha is going to be 1. And there we go. And now you can see that there's this little pulsating, flashing thing. It's a little subtle, so maybe I should increase it just for visualization purposes. So that seems to work. It seems like we have a wave that goes up a little bit to 0.3, then it stays black, so presumably it's going to negative 0.3, right? Because cosine is from -1 to 1, and then therefore it's going to go to negative values. Cool. Great. So then we can composite this and use this value in our health bar colors in various different ways. The thing we were doing in the graph was that we were simply adding this, so we can do plus flash. Okay, so let's see if this works. That does seem to work. We have a flashing health bar. And we can change the color, and it's going to flash in that color range instead of the other one, and so forth. All right. Might go a little bit too low and too high, since we're mostly going to use this in the bottom range eventually. So let's reduce the range. That's probably fine. So one thing that we should also keep in mind is that if we are adding to a color, like we're doing here, we're doing Healthbar color plus flash. And remember, this is a float value, so this is going to be swizzled to a vector 3. So it's going to make an RGB value out of the one X component of this. Whenever you add or subtract from a color, you will, in most cases, accidentally, usually, change the hue of that color. So sometimes you want to make sure that you still keep that hue and still have that pulsating effect. So sometimes what you'd rather want to do is you want to change the magnitude of the color rather than adding a flat value on top of it. So if we want to do something like multiply, then multiply is the way that you scale vectors, right? Multiplying by a vector will not change its direction. And similarly, if you multiply a color, it's not going to change its hue unless you go outside of the 0 to 1 range. In that case, it will, because of clamping, and you have limited amounts of colors on your monitor. But generally, if you multiply rather than add, you will retain sort of the color quality of that color. However, this is going from negative 0.1 to 0.1. But if we're multiplying, we want to make sure that we still retain the color whenever this is 0. We don't want to multiply by 0. We just want it to stay at the default color. So what we can do is that we can add 1 to that. So then it's sort of going to originate at 1. We can do that either in the flash itself or here. Doesn't really matter. So if we add 1, this is now instead going to be from 0.9 to 1.1, right? So if we then multiply by that, it's either going to scale it down by 10% or it's going to scale it up by 10%. So usually if you do stuff like this, the flashing itself is going to be, the flashing itself is going to look a little fancier and better. It's going to retain the color quality of the texture. Okay, there we go. It's a little subtle right now, so let's increase the amplitude again. There we go. So now when it's flashing to be brighter, you can see that it doesn't go to this pale white. Now it kind of retains the saturation of the color, and all we're changing is the value rather than the hue and the saturation, right? It's kind of a nice thing of just multiplying a color. Oh, if you want things to animate in the editor, if you go to, let's see, it's somewhere here, you can check a thing called animate materials or animated materials. And that way it's just going to animate even if you don't hit play. But this was not what we were supposed to do for this assignment. We were supposed to make it flash when you have less than a certain amount of health, right? So we don't want it to flash all the time. So let's bring back some of the previous code we had. We had the Healthbar color and the Healthbar mask. There we go. So what we can then do is, let's move the Healthbar color. So if we want to like bring the flashing back, we can do Healthbar color times equals the flash. There we go. So now only the Healthbar itself is flashing, and the background is still going to remain black. Okay. Someone is asking if there's a risk that values go beyond 0 to 1 when you multiply. Yes, absolutely. So right now you can see that the red is fully saturated. So there's a bit of a edge moving up and down here, right? So yes, that can happen. So it sort of depends on like what effect you want to have. If you want, you can of course offset this curve to never actually shoot beyond 1. So if you, in this case, if you also subtract the amplitude, then that would make sure that it doesn't go beyond 1. If you only want the flashing to darken, but sometimes it can be like an artistic effect that you want to achieve. So it kind of depends on what you want to do with your stuff. Okay. So we got this health bar. We wanted to actually flash when your health is below a certain value. You don't want it to flash all the time. So in this case, we want to add a threshold for that. There are different ways of doing this. It kind of depends on like how we want to set up the branching, or if we want to avoid branching or whatever. So we could just make a simple if statement. So if health is less than 0.2, which is 20% health, then we want to flash. We could do that if we want. In that case, we should probably move the flash in there. There we go. So now we've added an if statement. If health is less than 0.2, we multiply the health bar color by this flashing value, right? So then now you can see that it's flashing when we have low health. And if we increase this, it's going to stop flashing. So the gameplay equivalent of this thing is basically you just want to warn the player when they have low health so that they spot the health bar and the things are dangerous right now. How expensive are if statements in the shader? So in general, if your if statement varies a lot across your rendering, then it can be expensive. If your if statement pretty much has the same value across your entire render, then it's not much more expensive than like an add. So it really depends on what you're doing. In this case, the health value is going to be exactly the same across the entire render. So we're not going to have like divergence within the same rendering of this health bar. So it kind of depends on what your condition is. All right, neat. Any questions about that before we move on to the rest? Speaking of optimization, wouldn't it be cheaper if you just check the X value in the vertex shader? What X value? Oh, this one? So if you want to check the health bar mask in the X or in the vertex shader, you can't really do that in this case. So the problem is that this is either going to be 0 or 1, right? And the vertex shader is doing this on a per vertex basis. So the vertex shader can't check these values on a per pixel basis, right? So what's going to happen is that we're going to set this value it's going to set it on a per vertex basis, and then it's just going to interpolate between those things, which is generally not what we want. There are ways of sort of kind of moving this there, but oh, wait, hold on. This one is, no, wait, never mind. You can sort of move some of these things to the vertex shader if you want. Like we could move the flashing stuff into the vertex shader because the flashing is the same. It doesn't matter like where we are across the fragments. If we only have 4 vertices, check-in percentage as an X is going to be either 0 or 1. Yes. Something like having this in the vertex shader. You can do that if you want. The thing is that the output color you're going to have is going to be per vertex. So what's going to happen is that you will have 4 color samples. There's going to be 1 color here, 1 color here, 1 color here, and 1 color here. And then they're going to blend across this entire thing. Because if you remember the interpolation across triangles, it's going to do barycentric interpolations across that whole thing, right? This is with the previous one where you had 2 static colors to interpolate between. Oh, in that case, yes, you could do that. Because then there was a single color across the whole thing, right? But in this case, we don't have that because vertically, it's changing colors between everything we have in the texture, right? Okay, do we move on to the overachieving stuff? There it is. Okay, there were 2 overachieving things in this assignment. One was to add rounded edges. The other one was to add a border around the health bar. I'm going to be radical, and I'm going to now flip these 2 because it's easier to do it in that order. So, add rounded edges to the health bar. All right, so now I think it would be good to talk about a general concept that is very, very useful whenever you are doing shaders. It's sort of recently gotten very, very popularized because there are, it's a super useful thing whenever you're doing something like ray tracing. So there is something called signed distance fields. And signed distance fields is sort of just a fancy way of saying a distance to something. And that distance can also be negative if you're inside of it. That's sort of it. And checking distances to stuff is it's something you do a lot in shader code in general. But recently, this has picked up a term, SDFs. So it's a very, very useful thing to search for in case you want to do like a lot of distance checks. So we're going to start by looking at one of the most simplest SDFs you can work with. I don't know if we should make this in a separate shader. Actually, we should do that. Let's make a shader SDF example. Create a material. There we go. Create a quad. Okay. Fire up our SDF example. All right, we don't need textures. No properties. Okay, I guess I should really set up a template for this. I'm sorry, you have to go through this every time. Okay, almost done with the boilerplate removal of garbage I don't want. Neat, what a shader. All right, so I'm gonna start by just outputting the UV coordinates. So we're just gonna do return float 4 i.uv, comma 0, 0. There we go. Okay, so now we're looking at a very, very simple, simple square, and we have coordinates going from 0 to 1 on both axes, just like the regular UV coordinates we've been looking at. In many ways, we can think of this as a coordinate system, where every point represents the vector going from the origin of the coordinate space going to that point, right? So in some sense, what we're visualizing here is essentially a vector field, right? Every point is associated with a vector, which is the point itself. Okay, so like just with any other coordinate spaces, you can manipulate them. If you, for instance, if you multiply a coordinate space, you're scaling those coordinates. If you are adding or subtracting, you would be offsetting that space. So for instance, if we want to make this be 0 in the center instead of in the bottom left, then we can take these coordinates and we can multiply them by 2, for instance. So now we've scaled these coordinates. Now, instead of 1, 1 being up here, 1, 1 is now here, as in the vector with the components 1 and 1. And then we can offset these coordinates as well. So if we want to offset it to put 0 here, we can then subtract 1. So if we go back here, subtract 1, and then recompile. We now centered this coordinate space, and we've also made it so that 1 is at the very edge here. So now it's 0 in the center. We've got negative values on the left, negative values going down here on the y-axis, and then positive values in this quadrant, and so forth. So basically, we've now remapped this from 0 to 1 to -1 to 1. So let's talk about what signed distance fields are. Let's start with the distance field. It's basically the same thing, but a little bit less complicated. So what is a distance field? Just like this is a vector field that we're looking at, a distance field is one where every point that we're looking at represents a distance to something. So let's make a distance field for a point. In this case, let's make a distance field for 0, the point in the center. So a way we can do that is we can get essentially what we're doing is we're getting the distance value from, the distance from 0 to the current coordinate that we're rendering. So we're getting that distance. This is equivalent of just getting the length of that vector, right? So we can just do length of that UV coordinate, and then let's visualize that. So now what we have here is a distance field. Every single pixel represents the distance to the center, right? And this is how you make a radial gradients generally. So what separates a distance field from a signed distance field is that it's called a signed distance because generally distances are not signed, as in distances are never negative. But in some cases, it's useful to have that concept. Just like sometimes you have signed area, even though area technically should never be negative. Sometimes it's useful to have that. So one thing we can do to turn this into a signed distance field is we can just subtract some value. If we subtract 0.3, for instance, and then go back, then what's happening here is that we have values going up to 1 here, and then they go lower and lower, lower, all the way to 0 here. So now it's 0 along this boundary. But if we go further toward the center, it's going to start going to negative values. And since this is a distance field, this would be a negative distance, right? Hence the word signed distance field. So it's a very, very simple and common concept across shader coding. So what we now have is a signed distance field for a disk, right? Or no, actually not for a disk, specifically for a circle. So this is so now we have a way to distinguish if we are on the inside or on the outside. If we have negative values, we're on the inside of the circle. If we have positive values, we're on the outside. So this is a useful concept if you want to make any kind of procedural shapes and shaders, or if you want to use cutoff values and whatnot. So a simple use case for this is that maybe we want to draw something based on whether or not it's on the inside or the outside of this thing. For instance, we could make a step function. Step is basically a threshold. So we can do a step function between 0 and the distance, and let's just output that. And now, wherever the signed distance field is negative, we have black. Wherever it's positive, we have white. So, and what step is doing is basically the same thing as something like that. I don't know if the parameters are flipped. I always forget. Just flip the parameters if it doesn't work. Yeah, so it's a threshold check. All right. And then, as usual, as long as now we have a mask, we can do whatever we want. Like Oliver's mentioning, yes, we can make the Japanese flag out of this if we want to, because then we can just lerp between these using this mask, right? There are lots of interesting features of signed distance fields that make them really, really powerful as soon as you want to do procedural shapes, as soon as you want to do something sorry, I just completely forgot the thing that I was just going to say. Procedural shapes, you can use it in ray tracing a lot because it's a very, very good data structure or a starting point for both 2D and 3D, or not 2D, but 3D ray tracers can use signed distance field in a pretty efficient manner. Anyway, but the general gist of it is just a distance. That's pretty much it. It's a distance to something that can also be negative. So that's what signed distance fields are. Okay. So what we're looking at here is specifically this one. It's a signed distance field for this circle. But it doesn't have to be a circle. There are a lot of different things you can do. For instance, it doesn't have to be a circle. We can make a linear distance field. So for instance, if we, instead of doing i.uv, what if we do i.uv.x? Well, this is also a distance field, right? Instead of being a radial distance, this is a linear distance where these values here are negative. So it's a negative distance to this 0 point, right? And then it's a positive distance on this side. So like sign distance fields are not limited to like complex stuff. They're also like very, very simple sign distance field as well. It's just that we usually don't call it sign distance field because it's such a basic operation to just have subtract some coordinate. But yes, so that was a short primer on that. If you want to dig really deep into sign distance fields and ray tracing and all of that stuff, Inigo Quiles has a really, really good like resource on his website if you want to see like, you know, how do you make a sign distance field to a triangle, to a tube, or and so forth, right? That's the general concept. Okay, so why does this matter? Well, one of the assignments was to make rounded corners for our health bar. Although also, I think it's funny that it seems to me like none of you had the solution of just making a texture for this, but quite often making a texture mask is the correct solution because it's usually really, really fast to read a texture compared to doing things procedurally, which sometimes has a lot of other issues like with aliasing and whatnot. But yeah, anyway, so just using a texture for this that you draw in Photoshop or something would be a really, really fast and simple solution for rounded corners. Anyway, let's see if we can apply this concept to the health bar. I thought that was cheating. You know what? In video games, everything is cheating. If you can take shortcuts, that's usually the best thing to go, or the best way to go. But yeah, obviously you would learn more not using textures. So, all right. So let's see if we can apply this concept to the health bar. Let's see. That's the SDF example. Health bar. There we go. Let's see. In this case, we're going to start by just ignoring all the health bar related stuff because now all we want to set up is some way that can help us make rounded corners, right? Okay, so let's go to Photoshop for this because now it's really, really good to like think visually about these things and try to work out exactly what you actually want to achieve and how this might help you, how you might like more easily visualize exactly what you want to do. What you noticed with the sign distance field, the radial one that we had, is that it looked something like this, where we had some radial shape or a gradient, and then we can threshold that in order to get a clean shape like this. For the health bar though, we don't actually want a fully circular one. We want it to be sort of like a 2D capsule, or rather, yeah, like this type of shape, right? And if you try to think about what might this shape be a distance to, that might be a good question to ask. If you know what like sign distance fields are at this point, you can try to figure out like, if this is the distance to something, what is this the distance to? And what you might notice is that this is actually the distance to this line. So what we essentially have is a threshold for a distance field to a line segment, right? Specifically a line segment, not a line. A line is infinite mathematically, so sometimes it's good to clarify there's specifically a line segment. So doing this, we would actually get the shape that we want for the health bar, right? So there we go. So this is the puzzle that we need to figure out. All right, but we don't have this shape. But what we have is a rectangle, and the rectangle is sort of encapsulating this whole shape like this. So then we have a bit of a like math puzzle because while we do have the coordinate of every pixel being rendered, if we want to get the distance to this line, then we need to get the coordinate of the closest point on this line, right? So if we have the current coordinate of this pixel, then what we would want is the coordinate of this pixel. If we have the coordinate of this one, we want the coordinate of this one. And similarly, if you're over here, you want the coordinate of this, and so forth, right? So pick any pixel here, and we want the coordinate to the nearest point on this line segment. So how do we get that? There is a relatively straightforward way of doing this. It does get a little bit more complicated because our coordinate system is actually going from 0 to 1 on the x-axis, but it's also going from 0 to 1 on the y-axis, right? A little confusing to put it there. 0 to 1, and it's also going from 0 to 1 on the y-axis. So what we have here is a stretched coordinate system. And this is a little unfortunate because if it's stretched, then just checking distance values is going to get complicated, right? So we probably want to start by making sure that our coordinate system is uniform rather than non-uniform, right? Where we probably want something like this, where this is 1, and then 2, and 3, wherever this would be, and so forth, right? We want this to be uniform rather than non-uniform. So that would be kind of the first step. In this case, we did, in the assignment, you were to set the scale of the health bar to 0.125 on the y-axis, which is exactly an eighth. So what we need to do in this case, if we want to have a uniform coordinate system, is that we can multiply the x-coordinate by 8, which would then scale this so that it's from 0 to 8 instead. So then we would have 4 in the center, 2 there, and pretend this is uniform. This health bar is too short. Aspect ratio is a little off, but we would have the coordinate of 8 over there. Okay, so that would be kind of the first step of trying to make a uniform distance here, right? All right, so let's just set up those coordinates. Also thought that assuming the aspect ratio of the quad was cheating. Yeah, that's fine. And then the assignment became a little bit harder, and that's just good because then you learned something, right? Because then you basically need to get the scale of the object, and then you need to use that in your math. But generally the solution is the same. It's just that instead of hard coding it, you replace those hard coded values with the scale of the object, right? So let's start out by doing the same thing we did for the other one. So we want to return float 4 i.uv 0, 1. Okay, so now you can see that we have this coordinate system where y is going from 0 to 1. Oh, sorry. X is going from 0 to 1 across the entire thing, but probably don't want to do that here because now we want a uniform one and not a non-uniform one. Okay. So what we then need to do is that we first need to set up the coordinate system for this. So let's make that a separate variable so that we don't mess up the UVs for the rest of the code. So this is going to be the, what do we call these coordinates? I don't know what to call these. Chords, there we go. Just generic coordinates. i.uv, there we go. But we want to modify the x component of this. We want to scale that by 8 in this case. So we can do chords.x times equals 8. And then we can output those coordinates just to verify. And now it looks like the 0 to 1 range is square, right? And that's what we want because now we have a uniform coordinate space. And we can also verify that beyond this, it actually has coordinates that go beyond 1 by using the frac function. So that one basically subtracts the floored version of this coordinate, basically just returns the fraction. So this is going to show us in case it is repeating, in case it is continuously increasing linearly, which it is, right? Okay. So that seems to work. So then we now have the actual pixel coordinate. So looking back at this, we have the coordinate of all of these pixels in a uniform coordinate space, which is what we wanted initially. Now, the next step is to figure out how do we get the points inside of here, right? The y coordinate of this one is very easy. The y coordinate is always 0.5. Because it's a line that is horizontal, then y is never ever going to be anything but 0.5. So we can just hard code 0.5 into where the nearest point is. So that's relatively straightforward. Let's see, let's name it the point on line segment. I guess we can float 2, where the y component is going to be 0.5. Cool. X component, we're not entirely sure yet where we're going to set that to, right? But if we think about the coordinates that we have, this is going to repeat 8 times, right? I'm going to try to make this a little bit more close to the actual aspect ratio that we have. Okay. So we have 0, 1, 2, wait, that's a 3. I was thinking 3 at the same time. Okay. So now we want to get the x coordinate that kind of stops here, right? We don't want to go further than this point. And then for the end, we want the one that stops in the center of this square, right? But for any values in between, if we are at 6.5, then the x coordinate that we want along this line is going to be the same. It's going to be 6.5. It's the same as the x coordinate of the input pixel, or the current coordinate that we have. So pretty much all we need to do is to clamp the x coordinate on the x-axis to always be greater than 0.5. 0.5, but it also needs to be less than 7.5. So this is the range that we want to clamp the x coordinate in, and that way we would make sure that the coordinate we want to get out of this is always within this line segment, right? So the x coordinate of this one, it's going to be the same as the current coordinates that we want to check with, which again is this point right here. So that point would be the current coordinate that we're looking at. So the current coordinate, chords.x, would be the x component of the current one. If we just do chords.x, it's going to be the infinite line that just goes beyond, and it doesn't clamp at all. But we want to make sure that we clamp it at specifically these values, right? 0.5 and 7.5. So we can clamp that. There's a built-in clamp function. We want to clamp chords.x from 0.5 to 7.5. Again, I'm just hard coding all of this for now. I believe this is the order. I'm not sure if this should go last. I'm not entirely sure. Maybe, actually, let's look it up, because why not? CG standard library, clamp. Yes, the value you want to clamp is the first parameter. Cool. So we are now clamping this between 0.5 and 7.5. And so now we have the point on the line segment. So what we got is both of these points. So now we have this coordinate, which in our code is called chords, because that's the coordinate system where we can just get any point in this coordinate system. And we also have the clamped point, which is going to be the closest point on the line segment. So all we need to do now is check the distance between these 2 points. So that's going to be the start of our sign distance field. So we can just call that SDF, and then we get the distance between the current coordinate and the point on the line segment. And then let's output that SDF. This was not Unity, in fact. There we go. So now you can see that we have a distance field where each pixel represents the distance to the line segment in the center here, right? And given the scale of our coordinate system, where it goes from 0 to 1 here on the x-axis, Jesus Christ, what is Photoshop doing? So it goes from 0 to 1. Then we want to make sure that, or usually it's nice to normalize these things. So we probably don't have to, but I like doing that. So I usually like to make this go from 0 to 1 and to 1 over here as well for the distance values. Because it's nice to have normalized ranges for this. Because you can see that it goes to 0.5, it doesn't go to fully 1. So I'm just going to multiply this by 2. Wait, that does not go to... wait, why does that not work? Fascinating. Is it because I'm not multiplying the... Yes. That might be because it's alpha blended and I multiply the alpha by 2 and apparently that affects the formula. Interesting. I didn't know that alpha values outside of 0 to 1 actually had an effect. Okay, anyway, so we got the distance. Let's multiply by 2 up here instead. All right, so we have our distance. We scale it by 2 so that we have values from 0 to 1 at the very edge. Okay, so then what we want is we want to be able to cut off a part of this. Now we have a distance field, but we're not actually doing the clipping along the edges that we wanted to get our round health bar, right? So if we want to do that, then we need to do something more. But just like we did with the previous one, when you have a signed distance field, usually you have a distance to some primitive, in this case a line segment, and then you subtract what can be considered a radius or a distance threshold. And in this case, the threshold should be wherever this distance value is 1, right? That's along this boundary. So if we subtract 1, that means that it's now going to be 0 on this boundary. So now we have assigned distance field to this like two-dimensional capsule shape, right? And then we can threshold based on 0. We could also just do threshold based on 1 if we want, but usually this wouldn't be a signed distance field in that case, but now it is. So then we can do the same thing we did before, where we clip based on this value. So clip based on SDF. And that's it. So now we're going to discard pixels that are outside of this signed distance field, unless I need to negate this. Yes, I do. Now we did the opposite. So let's just flip the SDF, and there we go. So now we have a mask that can make rounded corners on our health bar. And then all we need to do at this point is that we just need to bring the rest of the code back. And we don't really need to change anything because this is already clipping the corners. So all of this is for rounded corners clipping. All right, so let's go back. And now we got our health bar. It's flashing as usual, as we defined earlier. And then you can still increase it and decrease it, just like before. And everything works as you would expect it to. Everything remains the same about the health bar itself. Yeah. All right. Any questions about stuff so far? If you want to round only the very corners, do we need to make a composite shape? You don't have to make a composite shape. You can basically do the same thing that we already did, but because what we were doing here was essentially clamping the x-coordinate, right? Where we didn't allow the x-coordinate to go beyond here. You could do the same thing for the y-coordinate. So then essentially it would be a rectangle. And then you get the distance to that rectangle. Although it gets a little bit more complicated because the rectangle needs to offset a little bit away from this corner. So you need to work out that math as well. But yeah, then essentially what you would get is, a shape that would be rounded along these corners. Okay, so then we got one more thing. So we should do the border now. That was the last part of the assignments. Basically, the last one was to add a border around the health bar. And the reason that I put this after doing the rounded edges is because as soon as you have a signed distance field, a lot of these types of things becomes very easy to do, because what we now have is a sort of a gradient, or again, a distance field that goes out from the center, and then we have an increasing value like this. And it also does that along this whole rounded section, right? So what we can then do is that previously we checked the threshold where the sign distance field is 0, right? But what if we threshold it where it's slightly less than 0? In that case, we can get another threshold that is slightly offset inwards by some distance, right? So what we then get is that we can get another mask out of this that we can then use to manipulate the health bar. We can blend in a color here, so maybe we want to fill it with black or something to add a border around the whole thing. And it really depends on like what type of effect we want to achieve. So if we go back to the code here, we have the sign distance field here. And then let's, after clipping, let's just output the sign distance field again. So return float for SDF and the alpha channel 1, or just set the alpha channel to 1. And then we go back. All right. So now it's just pure black, which is what we would expect because the sign distance field has negative values here. So what we can then do is that we can make another sign distance field for the border, where we take the original sign distance field and we add some value. Let's add a little bit more just for clarity. So then we can show the border sign distance field. And now you can see that we have 0 is offset into this health bar, right? And if we then want to turn this into a mask, we could just do the same thing we did before where we threshold that. So let's make a border mask, and we can threshold that based off of the border SDF. Probably need to negate this one too. Wait, why is this sad? Oh, step requires 2 arguments, right? That was in clip. And then we show the border mask. There we go. Although I kind of expected it to be the other way around. Flipped. There you go. So now we have a border around our health bar, or we have the mask for the border, but we aren't actually showing the border. Something else we might want to do, we might want to make some of these things tweakable. So let's make a border size parameter, because it's fun to tweak things. And probably don't want max value to be 1. Border size, we got that down. Yeah, so then all we need to do is add border size here instead of 0.3, which was a hard-coded value for the thickness of this. All right, so we got the border SDF as a mask, and we now have a parameter for the size of this border, if we want it to be really thin or if we want it to be thick. It's kind of nice to have these like more easily tweakable things if you want to like artistically be able to control these things. Then we want to use this as a mask to add a border around the health bar. Okay. So we have the border mask, and all we need to figure out now is how we want to apply it. I think that the easiest way to apply this mask is to just make it black around the border, or just multiply by that. Although right now the mask is inverted, so if we multiply, the health bar is just going to go black. So we might want to flip this back to being black on the edges. Oh, I just removed the mask. So this black on the edges and white in the center. That way we can just multiply this into the existing health bar, and it's going to be black around the edges. So we got the border mask, and we can just straight up multiply it in here if we want to. There we go. So just stack all the multiply. And again, when you multiply by a mask, wherever the mask is 0, it's going to be black. Wherever the mask is 1, it's going to remain the same color. It's gonna like be unaffected, right? Okay, there we go. So now we have border to our health bar. You can change the amount of health you have. You got the flashing when you're at low health. Yeah, so there we go. That was pretty much all of this assignment. You said I could remind you to talk about anti-aliasing. Is that still on the table, or are we running out of time? We still have time to talk about that. So one simple way of doing anti-aliasing when you do stuff like this is kind of like taking advantage of the way that the sign distance field works in and of itself. And because we have that distance value, we can deploy a really useful tool in order to make this anti-aliased. Let's see, I don't know if we can, oh, we can do that here. So let's find the camera. There we go. Wait, that's the wrong one. All right, zoom in. So now you can see that the border here is not like, it's very aliased right now. So you can see that we've got all of these wandering stair steps, and that's usually not great. So we probably want to do something about that. So one, a really powerful and weird thing that that shaders actually have access to is that you can get what's called a partial derivative of any values that you have in the fragment shader. And what partial derivative means is that, a screen space partial derivative. So what a partial derivative is that it's an approximation of the rate of change of whatever the input value you give it. So if you know how quickly this sign distance field is changing in screen space, you can use that as a way to kind of do a little blending depending on how far away you are or depending on how close you are. And these types of partial derivatives is actually how the texture samplers figure out what MIP level to pick in the textures as well. So it's a really powerful tool. And there are different ways of doing it. But generally, the idea is that you use a function called fwidth. It's a weird name. I usually think of it as like fragment width or rate of change of the fragments or something. I don't know how to rationalize this name. I feel like it's a weird name. So fwidth is a very simple way to get the rate of change, or actually an approximation of the rate of change in screen space of some value. If you do fwidth of the border sign distance field, then we get the screen space partial derivative of the sign distance field. I'm just going to call it PD for partial derivative. All right. So now we have the partial derivative. So we have the rate of change. A very neat thing that you can do when you have the rate of change in screen space is that if you have your original field that you had as an input to this, if you divide that by the rate of change in screen space, you're going to get that gradient go from 0 to 1 across a single fragment. So this is pretty much exactly what we want for anti-aliasing. So if we take our border SDF and divide it by the partial derivative, the mask is going to make it so that we have a range of 0 to 1 along that border. Now we might need to flip a few things because usually things aren't exactly as we want. Yep. So this one is now inverted. We don't want it to be inverted. And it's also not clamped because these values are now going beyond 0 to 1. As you can see, it's like oversaturating the green color here, and it's inverted. So first off, we need to clamp it. So we can saturate it, which means clamp. So if we go back, it's now clamped. And then we need to invert it because it also flipped in this case. And if you want to invert a value in the 0 to 1 range, you do 1 minus. And that's how you invert a color or a value. And then recompile, and now we have anti-aliasing. And it's still going to work on the edges here. It's going to look all crisp and clean. And yeah, so there you go. This has been very useful when making shapes. But yeah, it's a very, very simple, simple trick. Oh, and also the f-width is actually a shortcut for f-width is kind of getting the partial derivative along the x screen coordinate and the y screen coordinate, and then it's doing an approximation of the length of that vector, and that's what this one is returning. You can get more accurate screen space partial derivatives if you want. So you can do that using the ddx function and the ddy function. Yeah, so that would give you the separate ones for each axis. And if you want to make this more accurate, you can get the, I think this is the way you do it. You make this a float 2, so it's a vector 2 for the x and the y axis. And then if you just get the length of that vector, then this is going to be slightly more accurate than the built-in f-width one. Slightly less performant, but generally doesn't matter. So if you want like a slightly more accurate partial derivative value, then you can do this as well. Great. Okay. One more and I'm ending it. Okay, well, if you don't want to stick around for my stream because I say sometimes, feel free to leave. You don't need to be here in that case. Okay, there we go. I think that was all I wanted to wrap up for the health bar. So I think I've showed this to you earlier. I'm gonna show it again. So hopefully it's gonna work out. Compression is not gonna destroy it. My GPU is gonna struggle now as well. Oh, it's not struggling at all. But yeah, so this is an example of using sign distance field, or actually it's slightly more accurate to call this just a distance field. But in this case, this is a ray traced fractal. And so like this is the Mandelbox fractal, which is a relatively like popular fractal. And in this case, we are using a 3-dimensional sign distance field. Again, it's a distance to an object, and the object just happens to be a fractal this time. So yeah, so you can make all sorts of cool stuff when you have distance fields. In this case, this whole scene is a single triangle, or 2 triangles, and everything else is just done in the shader for the math here. You can change the parameters of the fractal, and it's all real time because there's nothing that, there's no geometry here that needs to update or anything, right? This is a fractal. There we go. Just wanted to show another example of what you can do with some sign distance field stuff. And if you want like the very short version of how this works, I'm gonna give you the 1-minute version of this. So what's happening is that we have a camera, and then we have 2 triangles. We're just drawing 2 triangles right in front of the camera. And they're just facing the camera at all times. In fact, we can go to the scene view in Unity. So you can see that it's literally just a quad in front of the camera. That's it. So we're just placing these 2 triangles in the camera, and the rest is done in the shader for this fractal. What's happening in the shader itself is that we have some shape. In this case, it's a fractal, right? And if we have a distance field to this, what we can do is that we can shoot a ray, or mathematically, we can kind of step into this 3D space. And if we know the distance to this shape, then this is going to be the closest distance for this whole thing, right? And given that we know that the distance from this point in space is exactly what we have here, then within, God damn it, Photoshop, you know what? I'm angry with you now. Then we know that this distance is safe to traverse into this whole space. So if we want to raycast then we know that the step we can take forward here is this distance, right? So we can step forward by that amount. So if we want to raycast into this 3D object, we can now step that distance. Then we can repeat that process. Now we have a distance here, and that's going to be somewhere around this radius. So then we can step forward that amount, and we know guarantee that this ray is not going to hit or intersect the object because we know that the closest distance was this, right? So you can keep doing this. You check the distance to the shape, and then you step forward by that amount, and so forth. So this is one way of doing ray tracing for inside distance fields. And then eventually you get really close to the shape, and then it's going to make smaller and smaller steps, and then you can count that as a hit once you've hit it. Although I bent this one, which is a little weird. But basically you do that for every pixel on your screen. So that happens for every fragment in the fragment shader. Then you keep iterating, and then eventually you're going to hit something, right? The thing she didn't say that might be non-obvious, you know the distance to the surface when sphere tracing, but you don't know the directions. That's why we iterate. Even if we knew the direction to the surface, that wouldn't really help that much. Because the problem is that we don't know when we're going to hit this surface. That's why we're doing this type of search, right? So it's more like we don't know how large steps we can take to the point where we go into the shape. We want to be able to hit the surface of the shape and not go into it. And then, like, using this type of data, you can then use various math functions to also, like, not only do you get the point at which it hit, but you can also get the normal of that surface. So you end up getting a lot of information that you can use to, like, shape these objects. So yeah, and then you end up being able to do stuff like this. So you can see that there's a little bit of a gloss highlight. There's some shading on this. And there's also fog, which is based on distance, and so forth. This is what's called raymarching, right? Yes. I keep mixing up raymarching and ray tracing, but yeah. Okay, so basically, it's a ray on every single fragment, and then we're getting this shape out of it. How does this look in the scene view? It looks like this. It's two triangles and a camera. The camera, you don't really need a camera to do this. I just hacked this into Unity because I wanted everything to be in world space. But yeah, so this is what it looks like in the scene view. So when you move around, it's just the quad is just moving and the camera is turning. It looks kind of silly. And that's it. Is there a good way to translate code on a shader toy to Unity's shader code, or are they the same? Some of the things are going to be different, like the external stuff. Anything related to time, the time variable probably has a different name, stuff like that. Otherwise, shaded toy is written in GLSL, so some of the functions have different names. So I'm pretty sure they're called like vec3 rather than float3. I think lerp is called mix. So like some of the names are going to get swapped out, but generally the math is the same, so it should be relatively easy to translate it. I'm pretty sure the shaders in the shader toy don't really have a vertex shader. I thought they were mostly, you just had a fragment shader and two full screen, or a full screen quad. That kind of sucks. I mean, in shader toy, you generally don't deal with meshes. It's very much a playground for fragment shaders. You might have meshes there. I haven't looked into it too much, but as far as I know, it's mostly about input data, fragment shader, textures, and that's about it. By the way, the health bar should take the border into account. With a very thick border and extremely low health value, the bar could be entirely black even though it's not 0. That is correct, yes. But in this case, it's mostly a shader course, and I don't care about making sure that the gameplay and the readability of it is at the top, so it's not a priority for me. Are you using unsafe code? Do shaders even support unsafe code? Oh, no. The leak wouldn't be just from the shader itself. It's because, like, assigning materials, if I, like, instantiate materials every frame in the editor or something like that. But inside of the shader itself, there's nothing can leak there, no. This one is tricky. I don't know how much I should go into detail on this stuff, because some of it relates to, like, render pipelines, and I know most of you are likely not going to tap into render pipeline stuff, but maybe. It's not super tied to the render pipeline, but kinda. But you know what? It's going to be useful regardless. So we have talked about a lot about the stuff that kind of just sets a color of the surface or modifies the vertices, and kind of just directly manipulating and setting pixel colors. Generally, most games do not just do this. most games have something called lighting. You know, the whole concept of light sources shining onto objects, making them brighter. There are shadows where light is not, and so forth. So let's talk a little bit about lighting and some of the basic ways you can implement lighting in your shaders. Now, in most cases, a lot of the lighting stuff is going to be handled by the engine itself. So this is mostly going to be an overview of kind of the approach that you take for implementing stuff like lighting. And in our case, we're going to limit ourselves to one light source, because as soon as you go to multiple light sources, things get a little bit more complicated. And then it starts tapping into stuff that depends on the render pipeline and how everything is set up. So we're gonna go for the relatively straightforward case of a light source. So how do you do lighting on surfaces? We're delving into the realms of Flowstorm's lighting? No, because Flowstorm is very much a hack. So I don't know if you'd want to go into that. But I can show how that works, and we can talk about it later if you want details on how it works. Lighting I'm going to talk about now is kind of the very basic versions of how to implement lighting. If you already know how to implement lighting, how to write those types of algorithms, you're probably going to think that everything I'm going to be talking about is out of date. And yes, it's going to be. I'm going to show you some of the older ways that we used to do lighting in games before we started shifting into using physically based lighting and shading. However, not all games use that, so it's still relevant to some extent, and it's also much easier to talk about and wrap your head around than going, all in on physically based shading. Let's start off with a very, very basic. Let's draw a circle. There we go. What a circle. Let's say you have some sort of sphere and you have some sort of light source shining on this. So let's make the Unity style light source. And in this case, it's going to be a directional light. So a directional light means that this light source is at infinity. It is extremely far away. So for all intents and purposes, the direction of the light source is going to be the same regardless of where we are, right? So all of these light rays are going to be parallel. We don't actually have a light source that's at this distance, because then we would get light rays in this direction. So in this case, we're going to talk about a light that is infinitely far away, kind of like the sunlight in a game. Usually when you do sunlight, you implement it as a source that's infinitely far away. So we don't care about distance, it's just a direction, right? When we think about how to light objects like this, then usually we want to get some sort of effect where it's light on the side where it hits, on the side that's sort of facing the light source, right? And then we want that light to fade as you get to the edges of the objects. And a lot of this can sort of be broken down into very simple math operations. So that's sort of what we're going to do. We're going to look into how to do this, this very simple lighting. I'm going to try to repair my... Okay, there we go. Okay, so generally, I'm oversimplifying it now, but generally there are two types of lighting that can fall on an object when you're implementing a single light source like this. Usually you have what's called a diffuse lighting. So that's lighting, that's the one that usually looks something like this, where the direction you're facing doesn't really affect the object, in which case this is for matte objects or for a matte shading on something. As in, it's not very shiny at all. This is kind of just like light hitting it, and if something is facing away from the light source, obviously there's not going to be any light on that. The second type is specular lighting. Specular lighting is stuff that is almost directly reflected into your eye or camera. That's usually seen as a gloss highlight. It can be a little bit blurry depending on how shiny the object is. It kind of depends. The gloss highlight is a little bit more complicated because that one depends on where your camera is. So we're going to look into both of these two types of lighting. Okay. So now we can try to think about how would we mathematically represent these things. So, all right, so let's say we have a direction to the light source. So let's make that yellow. And this might seem a little reversed, but usually when you are setting up shading like this with light sources, usually the direction to the light source is is the direction to the light source and not the direction from the light source to the surface. And this is usually called a light vector, or just L. You're going to see just the L everywhere. Sometimes you might see it as W with some suffix or whatever, but I like calling it L. That's just the direction to the light source. And then again, since we're rendering this from every pixel in the fragment shader, the direction to the light source would be the same regardless of where we're doing it, because in this case, we're interpreting this as an infinitely far away directional light, right? And then we can try to think of where do we want this to be bright and where do we want it to be dark. Generally, I presume most of you would intuit that the opposite direction should probably not have any lighting on it, right? This is pointing in the complete opposite direction. There's no light hitting that whatsoever, right? And then you can move around this and let's consider the perpendicular directions. So if you consider the perpendicular directions to the light source, these probably shouldn't have any light in between here, but as soon as we start approaching this direction, we want it to be more lit, right? So how much lighting should we add here? Well, we usually want it to be brighter where it's directly facing the light, and then we want the brightness to slowly decrease along this side here, right? And once we hit the perpendicular, it should go to 0. So if I start writing some numbers here, where if we say 1 is maximum intensity, and then we go around the circle where we want it to be 0 here, then we can sort of start like thinking about what kind of intensity would we want here. Well, this one is facing it quite a lot. This one is facing away quite a lot. So maybe 0.5 should be like somewhere here, and so forth. And then you start decreasing this somewhere here, 0.25 and so forth. So you get a gradient going from bright to dark. And obviously the direction doesn't matter here. It would be the same in the other direction. And if you're looking at this and you've had a math course with me previously, you might recognize what we're doing here. We have a vector here for the direction to the light source, and then we have a direction out from the surface that is kind of the slope, or not the slope, sorry, a direction out from the surface called the normal direction. So you have the normal vector. And the normal vector is going to start pointing away from the light source as we traverse around this one. Once the normal vector is fully perpendicular, like the red ones here, we don't want any lighting at all. So if we consider the dot product, that is exactly what the dot product is. This is like one-to-one with how the dot product behaves when you have two normalized vectors. So we have the light direction and the normal vector. And if we do the dot product between those two, so the normal vector and do the dot product, the normal vector and the light vector, we also want to consider the case where they're pointing away. In this case, we would get negative values, right? Because that's how the dot product works. We would get negative 0.25 and negative 0.25 and so forth, or 0.5. And then here we would get negative 1. So when we're dealing with lighting, we probably don't want these negative values around because we don't actually want the light source to be able to subtract from the other side of an object, right? So unless that's a choice you have in your lighting style, in which case that sounds cool and I encourage you to do it. But in most cases, we don't want negative values. So if we want to get rid of those, we can just add a simple little function of 0, and we do a max function of this. So what this means is it's going to pick the maximum value of either 0 or n.l, and that means that whenever this is negative, we're going to get 0. So basically, it's just a way of saying clamp bottom at 0. So you're going to see this pattern a lot. If you're searching around for shaders, then this type of max 0, n.l or some other lighting function is very, very, very common, just to like clamp away the bottom values. Isn't this why saturate is called saturate? I have no idea why it's called saturate. I think it's because saturate, you can consider it a value range that is fully saturated. You can say that if you have color values or whatever, if one of the color values has hit 1, you could say that that's a saturated value, as in it's fully filled up, right? I think that's where it's coming from, but still a shit name. shouldn't have been named saturate. It's frustrating. All right, so this is a very, very, very basic type of lighting, and this is called Lambertian lighting, named after someone called Lambert. So this is a model for diffuse reflections. This one has nothing to do with specular reflections right now. It's only, this is only for the diffuse reflections. All right, so let's implement this. Let's try this and see how it works out. Let's create a new material. God damn it, I need to set up a template. You know what, if I do this course with some other students, they're gonna get the premium version of this course, where I've already got a template set up. They would not have to watch this anymore. Wait, did I call it mesh input or mesh data? Data, I think, right? Trying to be consistent. Okay. Don't care about fog. No fog. Illegal. Right, so this one is sampling a texture. We don't really need that. Let's add a... no, we don't need a color. We're gonna do that later. Okay, so now we want to... now we need to set up the vectors we need in order to calculate the Lambertian, right? We need two things. We need the normal direction and we need the light direction. So let's first do the normal direction. That one we've done before, so it should be relatively familiar to you at this point. It's kind of mostly boilerplate just to pass things from the mesh data to the fragment shader. So we're gonna set up a normal direction, and that's gonna use the semantic normal. And that's from the mesh data. Then in the interpolators, we just slap in another interpolator and call it normal. And make sure it's a float 3 because it's a 3-dimensional vector. Great. So now, oh, we also need to pass it from the vertex shader to the fragment shader. So o.normal equals v.normal. Great. And then we can just output that just to make sure it works. So return float 4, i.normal, and alpha channel, doesn't matter, because we're not using the alpha channel in this. There we go. Let's add some objects. What is sphere? Let's add another object. Let's do a capsule. Okay. Wait, why? And let's do a cube. Beautiful. Look at these colors. So now we're visualizing the normal direction as a color. And again, you can sort of think of vectors as colors. It's very easy to just visualize them as such. And you can sort of tell the direction of it by the colors. So if it's pointing directly upwards, the channels are 0, 1, 0, which means the y-axis is 1, which means the green channel is 1, which means the color is going to be green. So that's why the top is green on all of these, because the normal is pointing upwards. So we got the normal direction. That one is now done. Sort of. There are some things we can do in case we want to be a little bit more accurate. No, actually, we're going to do that later because that's more fun. Is that local or world space? Currently local space. So if we want to transform this, oh geez, I always forget the name of it. Unity, normal, object to world normal. There we go. Thanks. Because it's probably better to have this in world space. Right. So now we need the light vector. Actually, let's set up the variable float3, n, there we go. Single letter variable names. All right, so we got the normal, and now we need the light vector. I think it's something like light position 0, and we also need to include one of Unity's stuff for their lighting. I forget if it's lighting or auto light. So I'm just going to include both, like a true professional. There we go. So these are Unity's built-in CG code snippets where you can access some of the Unity specific data, such as the light position, which Unity will populate automatically. I presume it's in auto light since lighting is very gray and sad. Okay, so I thought it was light position 0 or something. I don't know if a world space light position 0 would actually work. Let me just double check Unity's documentation. You can tell how often I use Unity's lighting. I thought it was light pos 0 or something. Oh, light, no wait, world space light pos 0. Okay, that is the one we want. Never mind, yes. All right, so this one is a little bit special because of the way that Unity's forward renderer is set up. So world space light position 0 actually can be either a direction or a position. So if you read the documentation, directional lights, if it's a directional light being rendered, it's a world space direction, and that's the one we're doing now. It's the infinitely far away light source that's just a direction. And that means that the W component of this float 4 is going to be 0. For other lights, the W component is going to be 1, and then you're going to get the actual position and not the direction. But the way that Unity works is that this pass, the first pass that you have in a shader, is always going to be a directional light. The base pass is always a directional light. You can't have point lights in the base pass. Technically, if you want to do this properly, you would have another pass, and this pass would run for each additional light source, and those can be either directional lights or point lights. But we just have a base pass right now. So we're just going to presume that this is always directional because it's always going to be a directional light. So technically, this is a direction. Okay. So this is going to be the L vector. And then I don't know if this is the direction to the light source or from the light source. I'm just going to debug that. So I'm going to output L. There we go. And then where's the directional light? Okay, so if we make the directional light point straight down, we have a vector that's green. So that seems to indicate that we're actually getting the light vector, as in the one pointing from the surface to the light source. So I turn it to the right, we should be getting a blue, and that we do get, and then we should get a red one in this direction. Yes, okay. So it seems like we have the actual light vector. And the light vector is just going to be the same across the whole mesh, because again, it's a directional light. We're not actually getting a direction to a point light source. But we now have that vector. So now we have the normal vector, we have the light vector, and now we can do the Lambertian shading. Might want to clarify, because the name is a little contradictory there. Okay, so this is going to be the diffuse light. That's what we're going to get out of the Lambertian. So we do the dot product between the normal vector and the light vector. And now we have the very basic Lambertian lighting. And this is a grayscale, it's just a single float value. So I'm just going to swizzle that out to a float 3. And let's go back to Unity. And we now have Lambertian shading. So if we rotate the light source, we can see that we're getting something that resembles a very, very basic lighting setup. Yeah. All right. Any questions about that so far before we go into the fancier parts of it? Did you use the max function there? Nope, it's not necessary yet because we're not doing anything else than drawing this. But yes, technically we should add the max function there. Usually the problems don't show up until you start like using this value for something else. But yeah. Oh, you can also use saturate if you want. Because clamping between 0 and 1 is going to be the same thing as doing a max 0 and then the dot product. So saturate also works. You can do whichever one you want. Are we going to get into normal maps? Yes. Would max be faster than saturate? I think saturate would be faster. Because I believe that on some GPUs, I think saturate has 0 cost. I don't know what platforms it was, or if that applies to all the GPUs, the modern ones, but according to Unreal Engine's tooltip, saturate's supposedly free on most GPUs, yeah. Yeah, as far as I understand, saturate is such a simple operation that it kind of takes that path regardless, and whether or not it applies it is the only thing you're changing. So it just seems to me that it's a kind of a pass-through thing, or it does a pass-through, but it also just outputs a clamped version of it. The next thing we're probably going to want to do after this, I would say, is probably to add some sort of color to this, right? Right now, we have ignored two things. We have ignored the color of the light source, and we have ignored the color of the surface. Right now, we presume the light source is simply like just 1 in intensity. The color is just white, and that's it, right? So we probably want to implement some of the other properties of the light source. So light color, there we go. Light color 0. Let's add that. So the diffuse light itself only describes the fall off depending on the normal, but we also want to color this. And if you want to color something by some intensity, you multiply it together. Because we don't want to add more light on top of something that already exists. We want to combine this. Effectively, the Lambertian shading is a mask that we then apply to the color. And the color in this case, we only need RGB, so XYZ. And that means that diffuse light is now going to be a float 3 rather than a float. All right, so now we got the color, and we go back to Unity. And now we can change the light color, and everything's going to follow. We can also change the light intensity, because the intensity is encoded in the color itself. So it just makes the color stronger, so everything already works out. We don't need to add any like separate intensity parameter or anything. So what we set up now is diffuse lighting. We don't have any specular lighting though. So this is kind of a basic, pretty boring shading. It's not shiny at all. It's only based on the normal direction and the light direction. So we don't get these like nice glimmering, like moving specular highlights as we rotate the camera. It's all kind of flat and very matte and very static, right? So what we need to do is add some specular lighting. Specular lighting is sort of when things start getting more complicated, especially if you want to go into physically based shading, which is a little too much for this course. We're not going to do that. I'm just going to talk about a little bit what it is after we've done this. So there are different ways of doing specular lighting, and the two most popular ones that we've been using before the physically based era was usually something called Phong lighting, and then there's another one called Blinn-Phong. And I think the Phong lighting is probably the most intuitive one, whereas the other one is a bit of a hack. It just so happens that Blinn-Phong generally looks more believable, whereas Phong looks a little wonky in some cases, but I think we're going to start with Phong lighting, because Phong lighting is a little bit more intuitive when you're explaining it. So let's do both, and then we can compare them. I'm trying to shuffle my notes around. There we go. Okay. What's the highest value UVX and UVY could reach? The same value as floats, so it's the same range as float. All right. So specular lighting. Again, it's easier to break this down if you go into a 2D case and start thinking about that before you go into anything else. So if we have let's see, we got the light source, and then we can consider some sort of point. Let's see, this point. All right, so we have the light direction over there, and then we got the normal direction of the surface. So that's the normal at this point specifically. Otherwise, as usual, the normal varies depending on where we are in the mesh, unlike the light vector in this case. And the final one is that we have the view vector. So let's say we have the camera over here. There we go. What a camera. Trying to figure out what would be a good view direction for the most illustrative example. There we go. Probably good. Somewhere there. It's probably going to be great. All right. So we have the light vector by the normal direction, and then we have the view direction. So the view direction is, again, a direction from the surface to the camera. Let's make that the view vector. Usually just V. Did I actually write light, normal, and view? No, I didn't, but okay, hopefully it's clear regardless. So now the Phong lighting works is that it presumes a perfect reflection. So if you imagine the light vector, you can sort of consider what would happen if we reverse this vector, we point it down toward the surface, and we bounce it off. If we bounce it off, we're going to get this direction, or something along these lines. So this is going to be the reflected or the bounced light direction, right? I don't really know what to call this one. Let's call it R, probably best. So this is the reflected light direction. And then what you do is that you do the dot product between the reflected direction and the view direction. So then what you're getting is essentially how close is the direction to the camera matching the exactly reflected direction of that light ray. So what we're essentially getting is, are we staring directly into the reflected light in a mirror, or are we looking slightly away from that, right? So essentially, if we want to do Phong shading, then, again, not as popular as Blinn-Phong, but it's usually a pretty clear example. It's easy to understand. So we got the dot product between the reflected light direction and the view vector. And I'm just going to presume that all of this is going to be clamped now, because generally you need to make sure they don't have negative values. So just pretend that I write that everywhere, because it's going to be a little messy to always type that in. So Phong, this is Phong specular highlights. There are some more caveats to this, so I'm going to get to that soon. But let's start implementing this, the very basic implementation. So this is our diffuse lighting. And then we need the specular lighting. There we go. All right, so what do we got? What do we need? We have the light vector, we have the normal vector, we don't have the view vector, we don't have the reflected light vector. So let's start with the view vector. So in order to get the view vector, we need two things. We need the position of the current fragment, and we need the position of the camera. You could take the forward direction of the camera, but that will not make a change across your screen, even though it should. So if you just take the camera direction, then that would be equivalent of using an orthographic camera. But in this case, we have a perspective camera, so we need to get the actual fragment position and the world space position of the camera. So we can start with the fragment position. So let's add another interpolator for that. So this is going to be a world position of the current fragment. And then we need to pass that through the interpolator. So O dot world position equals multiply the model matrix, or unity object to world, and then we pass in V dot vertex. So we got the world position there. And then, as usual, I like making sure that things work. So return float for world position. That's not what I wrote. Oh, sorry. I dot world position. I'm not used to having code completion for shaders. Alpha channel doesn't matter. Great. There we go. It is very blue. So seems to be getting green colors there. Move it to the origin. You can see that it seems to work. moves towards red on the x-axis, rotation independent. Okay, seems to work close enough. All right, next up is we have the world position, and now we need the camera position, and that's built in Unity. World space camera position. There we go. So in order to get the view vector, float 3, view vector equals, so this is going to be the direction from the surface to the camera. So we want to do camera minus the surface position. There we go. So now we got the view vector, and then as usual, debug this, make sure that it works. So now we should get a world space vector pointing toward the camera. So if we want to try to tell if this works or not, we can again look at the gizmo in the top right in Unity. Does this direction line up with these? So now it should point toward the camera, which is in the X direction. Should be green at the top, and should be blue on this side, which it all is, right? So it's all matching up. One thing we need to do though is that we need to normalize this, because now this is a vector going from the surface to the camera, but we want this as a direction. So normalize, and now we normalize this vector. Let's go back. Now it's a little bit more calm. It's not oversaturated. We can see that this seems to work pretty well. It's blue, green, red. All right. So the next thing is now to do the Phong lighting. No, actually, we need the reflection vector first. So float 3. Now we need the reflected vector reflected along the normal. So we got the reflection vector now, or we're going to calculate the reflected vector from the light source. There's a built-in function for this. Remember in our math course, we did the math for reflecting a vector around a normal manually, but that's built in shaders. Reflect, and then we're going to provide the incoming direction, which is the negated light direction, because the light direction is pointing away from the source, but to get a reflected direction, we need to reverse it first. So we're going to reverse the light vector, and then the normal of the surface, which is n. All right, so this should now be the reflected light direction around the normal. All right, let's debug this. Back to Unity. This one is a little bit harder to debug because now we're getting a lot of colors. But if we presume this direction right here, now the camera is sort of the light direction. And are these bounce to directions valid? It looks like it is, right? You would expect it to bounce upwards here, which they're all green. So that seems to make sense. And they should all bounce toward the x-axis once they're hitting there, given this angle, right? So that seems to make sense. And then we have negative values on the other side. So now we have the reflected light vector. And now for the actual reflection itself, we need to do the dot product between the view vector and the reflected light vector. So float 3, specular light equals the dot product between the view vector and the reflected vector. And then also can make sure to clamp it now that we have other colors involved. And so now we have the dot product between the view vector, reflection vector, and this should give us a very basic setup for specular light. So let's try it out. So we're skipping the diffuse part right now. We're only showing the specular part. So recompile, and there we go. So now we have a very matte type of specular reflection, but you can see that the reflection changes shape depending on at what angle we're viewing it. And yeah, but it still seems to be some sort of resemblance of a specular reflection. There's one more thing that we should do here. Generally, when you're dealing with specular reflection, is you also have the concept of glossiness. sometimes called roughness, which is just the opposite. It's basically a way of saying how smooth is this surface. Is it extremely smooth to the point where we have almost mirror-like reflections, or is it very matte? Does it have a lot of like microfacets that are making sure that the reflection is not mirror-like? So usually we represent that with a value for glossiness. So let's add that as a property called gloss. Here we go. So this is going to be the glossiness slider. And we're just going to make it a float for now. So we're going to set this at 1, because that's what we have right now. The way you usually apply this in order to change the way that the highlight looks, usually you use exponents for this. So you take your specular light and you raise it to the power of some gloss value. So specular light equals pow, which is the power value, raising some value to the power of some other value. So this would be specular light to the power of gloss. Although I didn't have a variable for this now. So gloss, there we go. Could also put that up here. Doesn't really matter. I just put it here now. So this would be, this is sometimes called the specular exponent. This value specifically, but we're just calling it gloss for now. Slightly misleading, but that's okay. All right, so we recompile. We can now tweak gloss. In this material. So if we increase gloss, you can see that the highlight gets smaller unless your cursor moves to another monitor or computer. And then we get a small gloss highlight. But there's one thing that you may have noticed that is happening now. Can one of you guess why this happens? There we go. Quiz for the class. Why does it look so faceted? The normal's not accounted for. The normal is accounted for. We are using the normal in the formula. We got it up here. N is the normal. We're using it in the specular lighting, and we're now showing the specular light. Double normals? No, I don't think we have any double normals. The normal's not used to smooth out the surface. Not by geometry, no. We could do that, but that's not what we're doing. The normal is still interpolated, so it depends on what you mean by that. I should probably just explain it at this point. Sometimes you can get away with this, sometimes you cannot. So in this case, we kind of ran into a case where we can't get away with this. Glossy highlights is one of those cases where you sort of need to do this correctly. So when you have some geometry, right, we have vertices, and then we have normals attached to each of those, then what's going to happen is that it's going to blend between these two data points. We have a normalized vector here, we have a normalized vector here, but if we linearly blend between these two, the normal we're going to get interpolated here does actually not have a length of a 1. This one is actually not normalized. So if we want to make this accurate, we need to normalize this vector to make sure that it has a length of 1. So what's happening is that the normal vectors we're getting out of the vertex shader is actually slightly shorter. And this is one of those cases where that shows up because now we're like, it's a very, very high contrast thing, and it kind of highlights this issue very clearly. So that's why we're getting this faceted look where things are brighter here at the vertices and at the edges. But when interpolating across the surface, the normals are going to get slightly darker because the interpolation and the interpolators don't know if this is supposed to be a direction or a position or just some value, right? So it's just going to linearly interpolate all of this. So that is why you get the this effect where it's bright at every vertex and between the edges, but then across faces it darkens. So you get like very obvious faces shown through this. So it's a pretty easy fix. All you need to do is you normalize the normal in the fragment shader. So now we're normalizing this on a per pixel basis. And then now it's going to be, now it's going to look fine. So if we go back, recompile, now it's a nice round little highlight. Okay, so now we got a very simple glossy highlight. Also works for this surface right here. It's just harder to see because this one is so hard-edged. Now we can go into compositing this, right? I don't know if we should composite this, like putting everything together, or if we should go into Blinn-Phong. You would really think the normals would be normalized. The thing is that the interpolators don't know what data is a normal and what data is not a normal. And in some cases, you actually don't want to normalize the normals. Sometimes you can do stuff like, it's a little hacky, but you can actually bake ambient occlusion data into your vertex normals, in which case you want them to be shorter. So yeah. So whenever you work with vectors, normalize them just in case. It's always a good idea to normalize them when you have to, because normalizing is not free. So yeah, it's good to do it where you have to. If you can get away with not normalizing the normal, then you might as well just you might as well just leave it on non-normalized if it looks fine in your game, right? Doesn't HLSL specifically require we say float 3 normal though? I don't know what it looks like outside of Unity, but in the mesh data, yes, you need the normal semantic, but in the interpolators, you don't. So I think it actually allows you to type normal here, but I don't think that actually makes any difference. I think that's just syntactic sugar for just adding more interpolators. But I could be wrong. I assume Unity's default shader do that by default. Probably definitely the PBR ones. Otherwise, I think it sort of depends on the platform. I think on some like mobile shaders, they're going to take a lot of shortcuts because you kind of have to, especially if you want like physically based shading on mobile. So it really depends on what shader you're looking at. What's the texture on the cubes on the bottom? Like these? Or it's grass and some rocks. I don't know if we should do Blinn-Phong or if we should continue this current thread. We should probably do Blinn-Phong, I think, because generally Phong is not really used very often. And the reason for that is that when you have a planar surface in any kind of surface that's just very flat, when you have Phong reflection with a very glossy highlight, Phong has a tendency to just be a circular shape. And that is generally not very close to the way that most surfaces behave. So because most surfaces don't have this like perfect mirror-like reflection. So generally you would get something that's more stretched along the direction to the light source. So there is another lighting function. This was Phong, specular lighting, but there's also something called Blinn-Phong. So we're gonna look into Blinn-Phong now. Ooh, I don't know if we can fit Blinn-Phong into... I don't know if we can fit that. We do have time for both. We're going to go through compositing as well. Let's just copy this whole setup. So for Blinn-Phong, we don't need the reflection vector. We're just gonna delete that. No more reflection vector. Okay, I don't know how to clean this up. Let's add a point. There we go. So the way that Blinn-Phong works is a little bit of a hack. It's kind of strange, the fact that it does work the way it does. And it's not very intuitive, but it does look better. I'm just gonna try to clean this up a little bit because otherwise it's gonna get cluttered. There we go. So the way that Blinn-Phong works is that it has another vector, which kind of a silly name, but it's called the half vector. So the half vector is a vector that is an average of the light vector and the view vector. And in this case, it kind of matters how long these vectors are. So I need to fix this up a little bit. There we go. So the half vector lies directly halfway in between the light vector and the view vector. So I guess it would be here somewhere. We got this is not halfway. I'm separating them a little bit just for readability. So now we get the half vector. So we have the half vector, and then the way to get the half vector is basically you take the light vector plus the view vector, divide it by 2, and then normalize. Or actually, you don't need to divide by 2. You just add the light vector, the view vector, and then normalize. And that's the way to get the halfway vector. We could write Blinn-Phong in terms of the existing vectors. So that would be the light vector plus view vector, and then we normalize that. I guess this would be the normalized vector hat thing. Normalize that, and then we take the dot product between the normal and this half vector right there. So we do the dot product with the normal direction. There we go. That's it. In other words, this is the same thing as the dot product between the half vector and the normal vector. All right, so this is called a Blinn-Phong. There you go. I cut off the hat for some reason. That's not good. All right, so I got Blinn-Phong. Let's try this out. So we don't need the reflected vector anymore, but what we do need is the half vector. So float 3, H, and that is then going to be the light vector plus the view vector, and then all of that normalized. There we go. And then basically everything else is the same, except we do the dot product between the half vector and the normal vector. There we go. So if we go back and recompile, you can see that this highlight is now anisotropic, which is the technical term for different on different axes instead of uniform in all directions. So it's no longer perfectly circular. Now it has a bit of a stretch to it, right? Which is closer to the way that things actually work in reality. This is very much a hack still, but even though it is a hack, this is closer to reality than Phong. So Blinn-Phong is usually the one that people opt to use for some of these more basic lighting models. Yeah, so that's Blinn-Phong. Otherwise, it looks very similar in many ways. There's one more thing we should probably do, and that is if there's a bit of an edge case when your camera goes at an extreme angle where the light source is sort of behind. You can see that we get this tiny little 2D spotlight looking thing at the very edge there. And this is because we currently don't cull this light depending on if we're behind something or not. So we can actually use this, use the Lambertian to remove this if we want to. So the Lambertian being the diffuse one where the light source is starting to fade away from you. You can use that in order to just cut it off so that it doesn't go to the backside. So if we want to prevent that, we can multiply the specular light by this Lambertian, which is currently not separated, so we might want to do that. Let's just call it Lambert, and that's this part. And then the diffuse light is Lambert, but it's also multiplied by the light color, while Lambert is just the fall off itself, right? So we're going to do, we're going to multiply the specular light by Lambert greater than 0. There we go. Because this one is going to evaluate to a bool, which is going to get converted to a floating point value, which is either 0 or 1. So if it's 0, we're going to remove all of this. It gets multiplied by 0 and it just disappears. If it's greater than 1, there's going to be 1 and it just multiplies by 1, in which case it's just going to look the same way it did before. So if we go back, recompile, we no longer have that weird spotlight looking thing. So now it actually disappears on the backside. Okay, so far we've talked about the specular highlight in isolation, but usually you want to composite these together. Because right now the diffuse lighting is gone, the light color is not taken into account anymore, and everything's just kind of it's just this in isolation, right? But we want to put this in a context where we have more stuff, right? I'm gonna remove that. Actually, you might want to keep that for posterity. Okay, right. So this is specifically Blinn-Phong. This is used for Phong. All right. There's actually one more thing we could sort of talk about. The way that gloss works is kind of annoying. Yeah, let's talk about this now because it's easier to tell what's happening. So you might be able to tell that if I set the gloss to 2, or something reasonable. This is a value of 7. If I pull this up to 15, it's somewhere around here. If I pull it up to 42, it's somewhere around here. And you can go very high on this before you get like a very tiny spotlight. So this gloss value is at 571. So it's kind of annoying to deal with this value range because you have a huge value range that's very non-linear. So usually when I have gloss values, I like to remap this value into an exponential curve. Because it's kind of annoying to have to like deal with these huge values and the very small numbers. So let's change this to, instead of being a float, change this into a range between 0 and 1. And then we want this to be remapped to some other range. All right, so if we want to remap this, then we can think of the specular exponent as a separate part of this, right? Because now glossiness is going to be between 0 and 1, but the specular exponent is going to be something completely different, right? So let's redefine the specular exponent based on gloss, right? So we're going to pass the specular exponent in here. And now we're going to use gloss to remap this to some reasonable values. So this can be done in many different ways. This is just a way that I personally like doing it. The way that I usually set up gloss is I do exp2, which is 2 to the power of the value you send it as an input. I usually do exp2 gloss times 6 somewhere, or 8, and then plus 1. There we go. So if we use this as a specular exponent, it's basically 2 to the power of this value. And then if we go back to Unity, we're now going to have something that feels much more linear than we had before. Actually, plus 1 should be outside of there. Wait, that barely made any difference. Plus 2 is better. Usually you don't want the very low ranges regardless. So just adding something is something you can do. Yeah, so now it feels a little bit more linear instead of having to deal with like huge values. I think I did times 11 as the default in Shader Forge back in the day, in case you want the really, really small highlights. But yeah, kind of a neat little trick. However, this is done in real time. You might not want to run this math in the like fragment shader. It's probably better to do this on the C# end, and you pass in, you do this in C# and then you pass in the higher value afterwards. So it's not the best thing for like optimizing stuff, but it's really useful. It also makes it much easier in case this is not uniform. So if you have a gloss map, for instance, this would be a texture and not a uniform value across the entire shader, in which case you couldn't even do it on the CPU. So it's just a nice little remapping value. exp2 ought to be cheap on floats though, I imagine so, yeah. Yeah, all right, cool. Let's move on to compositing. So currently our specular highlight does not care about light color, which it should do, right? Because we're sending some color in, we want to bounce that same color off of it, right? So we want our specular light to also be colored by the color of the light source, which I lost somewhere. Where is it? Light color. There we go. So multiply that by the light color. And then if we go back to Unity, then that doesn't matter because we are not making this we're just using the X component there. But this is a vector 3, so we want to use all 3 components because we're now multiplying a color into this. There you go. So now specular reflections are now based off of the light source. That is a gross yellow. All right, so we got the specular highlight down. There we go. Wait, What is this one doing? Oh, it looked like this one had incorrect colors. Anyway, right. So now we got the specular lighting set up here. And now we need to composite these together, as in we have diffuse lighting, we have specular lighting, and we also want a color of the surface. So let's do that. Let's put everything together. So adding the lights together, you can simply do diffuse light plus specular light. Because we don't want these to like multiply the other. We don't want one light to dampen the other. We want them to be able to like just be added together. If something is specularly reflected off of something, the diffuse lighting underneath should still be there, right? So we want to add specular light on top of the diffuse light. So if we go back to Unity, we now have the diffuse light as well as the specular highlight from this, right? So now you can see we have the combination of both, and one of them changes with the view direction and the other one does not, right? All right, and now we also need to add a color of the surface. So let's go back up here. Let's call it color. It's not a range. All right. So here we get into a little bit of like technicalities of how surface reflections work. I'm very much oversimplifying things, but the way that it usually works is that if you have diffuse lighting on something, the diffuse light is going to be affected by the color of the surface. So if we now go back and we give this some sort of color, multiplying the diffuse by that color generally gives us the result that we want. So now we have, you know, red surface, or maybe we want a blue surface, and everything still works the way that we would expect it to. Then specular light, however, should not be multiplied by the color of the surface unless it's a metal object. Because metals tend to reflect light a little bit differently than like plastic, for instance. So usually, if you want things to look a bit more plastic, you generally don't multiply the color of the surface by the specular light. But if it's supposed to look metallic, then usually you do want to multiply the surface color there. This gets way more complicated if you want to start trying to do even more physically accurate model. So I'm heavily simplifying this now. So generally you want to leave the specular light as a pure reflected light, and you don't want to actually change the that light based on the surface color. But yeah, so that's a very basic implementation of light sources. Any questions so far? Is the specular highlight that prominent usually? Depends on the object. Like some objects have very like intense specular highlights, some don't. So it really depends on what it is, what type of surface it is. Is it very smooth? Is it not very smooth? Yeah, it depends. Like if you have something like shiny cars or water, or anything that's polished, like polished metal, polished plastic, polished wooden tables, like all of these things tend to have this very, very sharp specular highlight. Does PBR not use Blinn-Phong plus Lambert shading? No, very much not. So PBR, well, actually you can if you modify it. There are ways of making these models a bit more realistic. There are a few concepts that kind of got introduced with physically based shading or physically based rendering or physically based lighting that you can implement on these things too. So here's a bit of an overview of a generalized concept of what we're talking about. We have some surface, right? That's great. We have some sort of light source somewhere, and there's a light ray shooting into the surface, right? Then if you want to visualize what diffuse lighting is, as in diffuse lighting was what we were talking about here with the Lambertian, Diffuse lighting is uniform in all directions. So if there's an incoming light ray, then if we want to try to quantify how much lighting is bounced off in either direction, then diffuse lighting means that the amount of light coming out is uniform in all directions. There's some amount of light just uniformly spreading in every direction. So sometimes you can visualize that by this little lobe, kind of like being a shape for where the light is going out after a single ray is incoming, right? Specular reflections work a little bit differently. Specular reflections are very strong when they're reflected, but they weaken when they are further away, right? So usually those look something like this, right? If it's not very glossy. If it's very glossy, then usually it tapers off very quickly. And then these are called lobes, like specular lobes. So usually it looks something like this. If you want to draw the outline of, the vectors coming out of that reflections. And then you can combine both of them. You have diffuse lighting that's going to be spreading like relatively equal in all directions, but then you're going to get a spike for where the specular lobe is sharp and pointing out at the reflected vector. And then that's going to taper off, and then eventually you're going to get something like this. So then this is the reflected direction. And so basically what we're describing is, in this case, we would have a camera here, right? Basically what we're describing here is called a BRDF. This is a word that means bidirectional reflectance distribution function. Basically what it means is that we have some function that takes a light source input that then spreads light in various directions. And how it spreads these lights is defined by the BRDF. So we did set up a basic BRDF here. We have some incoming light, we have the Lambertian for our diffuse light, and we have the Blinn-Phong for the specular light. All right. Yes, this is a little bit penis-like, but you know what? That's okay. We're all adults. So, all right, and this function can look different depending on what type of surface it is, right? So in this case, it has both a glossy highlight, right? It has a glossy highlight, and it has a diffuse spread here. But that's not necessarily the case, and it also depends on what kind of surface this is, right? So one of the concepts of physically based shading is called energy conservation. Oh yeah, it does look like a duck. That's true. So one of the concepts of in physically based shading is that you have some amount of incoming light, right? As soon as you get into physically based shading, you usually start getting to use like symbols like this, where it's really confusing because then the other vectors are also called that by something else. I don't know. But basically, you have some incoming light, and what energy conservation means is that when this is bounced off, it doesn't create additional light. This is something that can get kind of complicated, because what that means is that you need to make sure that the sum of all of the outgoing rays in both your diffuse spreading and the specular reflections, all of that needs to not go above 1, and anything that's less than 1 needs to be considered an absorption, right? As in, light comes in and the surface absorbs some amount of that light, and then some light bounces off of it, right? Diffuse bounces in all directions, specular bounces in this direction. But if you sum up all of these vectors, the idea of energy conservation is that they should all add up to 1 in case everything is reflected. But if some amount is absorbed, it can be less than that. What we have done here is definitely not energy conservation. So for instance, if we change the gloss, the amount of light that gets reflected is way more when we have low gloss then we have high gloss, even though theoretically this should only bounce off the same amount of photons. We shouldn't add more light just because we have a more rough surface, right? So one of the concepts is energy conservation. So if we want to make a very, very bad estimation of what this looks like, we can take the specular light and multiply it by gloss. This is not the way you're supposed to do this. This is just an approximation. But if we do that, you can see that as it gets glossier, it collects more light in one spot. And when you reduce the glossiness, the light spreads out. So it's much weaker, right? So that's a way of like approximating this behavior of energy conservation, right? With PBR, do you need to calculate bounces? No, PBR, so any BRDF doesn't really account for bounces, but some of them are based off of bounces. There are many different like methods of calculating this, but basically what many of the BRDFs do is that they presume that the surface on a microscopic level looks a certain way. So for instance, you might presume that you have a surface that has these V shapes in it, for instance, because generally on a microscopic level, surfaces are not perfectly flat, right? And then what you might do when you try to work out a mathematical formula for a BRDF, you consider what would happen to light rays coming into this situation. And then you start thinking, well, okay, if it's hitting directly on, it might bounce like this, right? So if we consider these perfectly specular, then we would get certain behaviors depending on the angle that the light is coming in. And so there are models that presume that these are perfectly specular. There are models that presume that these are perfectly diffuse. And that also means you need to take into account occlusion, where like any light coming from this direction wouldn't hit down here. It would only be able to hit up here. So there are all sorts of effects that you can get out of this that you can do a bunch of math functions on. You can read up about them. They're called like Cook-Torrens function, Oren-Nayar's diffuse reflections. There are many, many, many different physically based shading models out there. And Unity's built-in shader and Unreal's built-in shader, all that stuff is physically based. Pretty much everything is physically based by default these days. But I think it's useful to talk about how to write these just to get a general idea of how do you write functions like this? What's a starting point? What's a BRDF? And so forth. So physically based rendering in and of itself is generally a broader topic than just the surface lighting like this. There you go. BRDF. Oh, Jesus Christ, it embedded a huge thing. Please do not. Yeah, so you can read about those there. A bunch of the models are listed there. The Lambertian, the Blinn-Phong, and Cook-Torrens, and all of that stuff. So, yeah. But they generally get way more complicated. There's one more thing I wanted to talk about related to this. Just as an aside, the way that Unity's forward renderer, the built-in forward renderer works, is that for any additional light sources, there's one more shader pass. So there's an extra shader pass that's called a light add shader pass. So whenever something is rendered with the Unity's legacy forward renderer, then it runs an additional shader pass for every additional light source. So if you have 4 light sources around a mesh, that mesh is going to render 4 times. So in that case, basically what it does is that it kind of skips anything that you only want to do once on a shader, but it renders additional light sources additively on top of your existing render. So you would have pretty much the same code, except you need to handle directional versus point lights, and then you would pass that into the second pass. But it's a little legacy. Most people don't use the legacy render pipeline, or actually maybe most people do. So I don't know how relevant it is to add support for that now, but yeah, that's pretty much how it works in that case. Oh, someone asked a question. Sorry, I missed that. Is it possible to use shaders for creating a glowing orb like in this picture with a light and aurora around it? If so, could you show it? Yes, so usually that looks like you would just use a sprite for that. Like the general effect of that is it's sort of a combination of a bunch of particles if you want to get the smoke effect around that. There could be a sprite in the center that has a very, like just an additively rendered quad with a flare. And then the lines going off to the side, those are in almost all cases done using textures as well. And if you want to search for resources on this, anisotropic lens flare, and then you will find it. Very popular in sci-fi genres. I think Mass Effect, it was like a core thing in the Mass Effect series. They used anisotropic lens flares everywhere there. But yeah, so if you want a keyword to search for, that would be the one. Could you take this shader and use that as a mirror, or would you need a completely new shader? You would need a completely new shader. Making a mirror is much, much, much more complicated. It depends on how you want to make that mirror. More specifically, it depends on what you want to be visible in the mirror and whether or not it should be dynamic or non-dynamic. The only thing that is visible in this mirror is the point light right now, or our directional light, right? Nothing else is visible. There are other aspects of lighting where, for instance, we haven't talked about image-based lighting, which if you've used Unity's reflection probes, basically those provide the data for image-based lighting, where you kind of bake a cube map or an environment map, where you save data about the way that the environment looks, you bake that into a texture, and then the shaders read from that cube map, both for diffuse lighting and for specular lighting. That's almost always used for chrome, for instance. Anything chrome uses that. Anything that's remotely shiny uses that these days. So yeah. When we say legacy pipeline, does that mean anything that isn't HDRP or URP? I mean the built-in pipeline, the one where you just start Unity and you don't select any of the render pipeline. Is that what they do for scope reflections? Almost certainly, yeah. Cube maps and environment maps are super, super popular for anything that's like supposed to reflect the environment. It doesn't do real-time reflections though, but it works very well in many, many different cases. Did you use forward rendering and budget cuts? Yes. Deferred rendering relies on screen space textures. Deferred rendering means that you need a lot of video memory in order to have that. And given that VR is already so high resolution, we didn't want to use deferred rendering for that reason, because we're going to need like a ton of video memory just to cover the amount of pixels in a VR headset, right? So this is forward rendering. This is not screen space based at all. Another difficulty with deferred rendering is that you can't use MSAA, like multi-sample anti-aliasing. And anti-aliasing in VR is really important. So an MSAA is one of the best anti-aliasing algorithms out there. So like in terms of like how good it looks and how much it costs. Whereas if you use deferred rendering, you pretty much always use one of those like shitty anti-aliasing algorithms that kind of makes all of your textures also look smudgy. Generally, like you have to like sort of hack around it. But with forward rendering, you can use MSAA, which looks super good. And like dynamic lighting was not really a big priority for us. The biggest feature of deferred rendering is that additional light sources are almost free, but additional light sources in forward rendering is really costly. So usually when you're in a forward renderer, you're limited to like 4 light sources per object, because if you go beyond that, it tends to get really expensive. Or you need to like cut down the way that they are rendered. So additional light sources might be per vertex instead of per fragment. So it really depends on the case and what your requirements are for the game. But generally that's the trade-off. Deferred rendering, you can have like tons of light sources. They're almost free. And in forward rendering, you get really nice anti-aliasing. Light sources are expensive, but everything looks really crisp. Forward rendering also means that you can have any kind of lighting on any object. Whereas in deferred rendering, you sort of need to unify the way that lighting works, that everything needs to be lit the same way. And anything on top of that would have to be like exceptions. And transparency also generally gets complicated in deferred rendering. Not always, but usually. Okay, sorry, that was a long rant about deferred shenanigans. Sounds like deferred rendering is always inferior. Oh, definitely not. Deferred rendering, like I said, deferred allows you to have like however many light sources you want, pretty much. Like that's the advantage of deferred rendering. And yeah, it's also deferred rendering, or Usually like deferred prepass or clustered forward rendering is usually the way that people go now. But yeah, with no extra performance costs. So I don't know if you know about big O notation, but the expensiveness of adding light sources in deferred rendering is linear. The expensiveness of adding light sources in forward rendering is non-linear. It's exponential because you have meshes, or every mesh needs to be rendered an extra time for every extra light source. So things grow much faster in forward rendering. But in deferred rendering, you can just slap a bunch of light sources in there. And again, I'm simplifying things a lot right now. There are many different types of deferred rendering. There's like deferred prepass and whatnot, which is a little different. But anyway, right, there was one more thing I wanted to talk about. We were looking at some screenshots at various games, and specifically in Overwatch and in Dark Souls. There was some effect that was called a Fresnel effect. So I think we should wrap this up with just making a simple Fresnel shader. So usually Fresnel, in terms of the artistic effect, not the physical phenomena, don't mix them up. So usually if you're reading about like physically based shading, there's usually several terms. A Fresnel term is usually one of the things that are included in your physical based shading model, but both the artistic effect of Fresnel and the physically based lighting version of Fresnel are both related to when your camera has a very low grazing angle towards the normal of a surface. So yeah, so if you want to do a Fresnel effect, that is very straightforward. So let's do a Fresnel. The only thing you need to do is the dot product between the view vector and the normal vector. And then if we return that, we got the Fresnel effects. So if you want to do this for like item highlighting or something, you would generally want to first invert it so you have glowing around the edges. So now you got this, and this should be a familiar effect at this point if you've seen this type of glowy thing. Yeah, and then if you want this to be like, I don't know, something that you're going to use in as some sort of effect. Maybe we'll do something like this, and then you would add the Fresnel on top of that. And now it's like some sort of flashing indicator of something. That looks horrible. Let's use a cosine instead. Oh geez, I hit negative values. RIP. But you get the idea. Do you recall where the Fresnel was used in Dark Souls? Yes. Yeah, V is the view vector. The direction to the view or the direction to the camera. But yeah, so it's, could probably just dig up the Fresnel thing. Here you go. So this is, you can see that this is the same concept. You can see that it's like glowing around the edges of wherever the normal starts facing away from you. It works really well on very round objects, right? Doesn't work as well on like hard edges. It doesn't actually create an outline, but you can sometimes use it as a bit of a hacky substitute for it. Very commonly used for like highlighting objects. This is an example in Overwatch, also using Fresnel. You can see that Roadhog's belly, as it like curves away from us, you get a stronger highlight, and then it fades toward the center, right? So it's the same idea. There's another one in Overwatch. Tracer, teleporting is all full of Fresnel. To make an outline, could you use Fresnel and step? To some extent, but you wouldn't get an outline on hard-edged objects, which is, again, the downside of this. So if we go back to this code, we could, of course, threshold this. So we could do step on our Fresnel, threshold it at 0.9 or something. So you sort of, kinda get some sort of outline, but usually doesn't look very good. So it works like the only like good case for Fresnel is specifically like a sphere. But other than that, you can see that you start getting like artifacts that you usually don't want for this. So it's a very like naive way of doing this. It works well for smooth objects, not as well for objects like this one, right? I think that's going to be it. We definitely don't have enough time to get into normal maps, so we're going to do that tomorrow. Do you want an assignment? I should just ask. Would you like something to do before tomorrow? How about make this shader have compatibility for multiple light sources? How about that? The thing I mentioned about having a second pass, I think it would be good to learn about how that works if you're interested. I'm gonna try to not help you too much on that. And this might force you to do some Googling and some sleuthing and interneting. And you might need to look into Unity's built-in shaders, which is what I usually do for whenever I want to match Unity stuff. Yeah, so how about that as an optional assignment? I think that's going to be it. Oh, things might get complicated for light cookies. So you can ignore anything related to light cookies if you want. Or spotlights in general might be complicated. I forget how they work, but it might be. Thank you all for today. Hope it was useful.